Hello and welcome to this video. So in this video I will be taking you through the 2020 AMC 8 math competition and I'll essentially be taking the exam for you guys, but throughout it I'll be providing my solutions, perhaps some alternative solutions, and hopefully with these solutions you'll be able to gain a better sense of how you should be approaching some types of problems, what things to look out for, and I think this will be a really good learning opportunity for people of all ages, especially those who are preparing to take this exam. So this will probably be a long video because I'll be talking through each problem a lot, so sit back, relax, and enjoy, and hopefully you'll learn something. So we'll start with question 1. So question 1 says that Luca is making lemonade to sell at a school fundraiser. His recipe requires 4 times as much water as sugar and twice as much sugar as lemon juice. He uses 3 cups of lemon juice. How many cups of water does he need? So when we see a question like this, where we're trying to determine an unknown quantity of something, in this case water, when that quantity is unknown, we're prompted to use variables. So let's start by doing that. Let's start by defining a variable for the quantity that we're trying to find, and then we'll solve for that variable eventually. So we'll let W be equal to the number of cups of water, because this is what we're looking for. If we can somehow create some equations and solve for this letter W, we'll solve the problem. So I often like to look at this last sentence here and then create a variable based off of that. Okay, so we see that, all right, let's look back in the question. We see water is mentioned here, and in this sentence, there's a relationship between water and sugar because the recipe requires 4 times as much water as sugar. So let's also create a variable for sugar. So let S be equal to the number of cups of sugar. And okay, we've done a good job of using, let me change my colors. 4 times, we've used this much. But there's also this little bit here, twice as much sugar as lemon juice. So there's also this other quantity of lemon juice. So let's also create a variable for that. So we'll let L equal the number of cups of lemon juice. So we've done a good job of defining our variables. Now we have to somehow relate all 3 of them in some way, so that way we can solve for W. So let's start at the beginning here. The recipe requires 4 times as much water as sugar. So we're going to have some sort of relationship between W and S. So the amount of water is 4 times the amount of sugar. So we can say that W is equal to 4S. And the way to think about this is suppose we had 2 cups of sugar. Then we need to have 4 times as much water, so 2 times 4 is 8, and all of that is represented in this equation here, since we don't know how many cups of sugar we have at the moment. And now we'll take a look at this part right here, twice as much sugar as lemon juice. So we can do a very similar thing here. We need an equation that represents a relationship between sugar and lemon juice. There's twice as much sugar as lemon juice. Twice is the same thing as 2 times. So it's a similar thing here, except now S equals 2L. Cool, so we have these 2 equations, and we're also given, he uses 3 cups of lemon juice. So already we know the value of L. We're given that L equals 3. So remember, we're trying to solve for W here. We can solve for W if we know what S is, because we just multiply S by 4. Well, we can solve for S using this equation if we know what L is, and we so happen to know what L is. So when L equals 3, this means sugar is equal to 2 times 3, which is equal to 6. And then if we go back to this equation here, we get W equals 4 times 6, since S equals 6. And if we multiply those together, we get 24. And that will be our answer. So our answer here is E. So the main takeaway for this question is if we're finding an unknown quantity of something, in this case, how many cups of water, we should be prompted to use variables and then determine equations that relate all of our variables together. That's problem 1. Let's move on to problem 2. So 4 friends do yard work for their neighbors over the weekend, earning $15, $20, $25, and $40 respectively. They decide to split their earnings equally among themselves. In total, how much will the friend who earned $40 give to the others? Okay, so there's a couple of aspects to this problem. First of all, the earnings need to be split equally amongst themselves. So however much money each person has at the end, which we'll find eventually, that the sum of all of those quantities of money should equal the total amount of money, because that's how the earnings are split, and all of those individual quantities should be equal. Okay, so what exactly does that mean? Let's say we have person 1 here, person 2 here, person 3 here, person 4 here. And currently, they each have these amount of earnings as given in the problem. And so they're going to, take all of their earnings, somehow divvy it up once again. But the main thing is each of them should have an equal amount of money after the split. So we'll just say, since it's an unknown quantity at the moment, an unknown quantity, we'll give it a variable. So let's just say each of them earns X dollars. So that means the sum of these 4 X's should equal the sum of their earnings, because none of the money is going to waste. So let's form a little equation here. We have X plus X plus X plus X. That's after they split the money amongst themselves equally. So all of them get X, it's equal. That should equal the sum of their earnings, which is 15 plus 20 plus 25 plus 40. And now we just need to solve for X, because that's the quantity that each person will have after they split the money. And so we're not quite yet solving for what the problem is asking, being how much money will the friend who earned $40 give the others, but we can determine that after we know how much money that person should have. If we know how much let's say this person should have $30. At the end, all of the friends have $30. Then we know that, okay, the person who has 40, they need to give away some of their money to get to $30. In that case, it would be $10. But that'll be the second step. First, we need to figure out how much money should they have. So that's what we're solving for here. So on the left-hand side, we get 4x. And on the right-hand side, we can add them up. 15 plus 20 is 35. Plus 25 is 60. Plus 40 is 100. And then divide by 4 on both sides. And we get x equals 25. So each person, after the split, should have $25. Let's just double check that. So we're saying these should be 25s. And again, this works, right? Because this top part here, it sums to 100. We just computed that here. And here, 25 plus 25 is 50, plus 25 is 75, plus 25 is 100. So all of the earnings are used, and here it's an equal split. So now we consider this person who started with $40. They have to give away some of their money to reach this 25. How much money do they have to give away? Well, that's an unknown quantity, and so we're going to solve for it. So we'll let y be the amount of money that, I'll just call this person D, that person D gives away. So the person starts with $40 and they need to reach $25. And they're giving away some quantity of money. So we are removing money from them. So we're going to subtract out the amount of money that the person is giving away, right? And now it just remains to solve for y. So we can add y to both sides, and we get 40 equals 25 plus y. And then we can subtract subtract 25 on both sides. So we get 40 minus 25 equals 25 plus y minus 25. 40 minus 25 is 15. And on the right-hand side, we have y. So the person is giving away $15. And that will be our answer. So again, we're dealing with some unknown quantity. In this case, there were two unknown quantities. First was how much money does each person have after the split, and the second was how much does the person have to give away. So we're seeing a common trend here that create variables for unknown quantities. Let's move on to question 3. Carrie has a rectangular garden that measures 6 feet by 8 feet. She plants the entire garden with strawberry plants. Carrie is able to plant 4 strawberry plants per square foot, and she harvests an average of 10 strawberries per plant. How many strawberries can she expect to harvest? So I like to draw pictures, helps me think. So we have a 6 foot by 8 foot garden here. And we're trying to solve for how many strawberries can she expect to harvest. That quantity is unknown. Let's perhaps create a variable. Now, it may not be the case that every single problem will require a variable, but it's a good first step in case you don't really know where to start. So we'll let s, actually I'm just going to move this to the left here, and we'll define some variables. So we'll say let s be equal to the number of strawberries she can expect to harvest. And similar to the first question, we can solve for s if we have some equations. Right now it's just an arbitrary variable. There's no numbers associated to it, but we're given a lot of other information in the problem. So let's see what we can do with that. So where else are we seeing strawberries? Over here, we see that there are 10 strawberries per plant on average. So perhaps if we determine the amount of plants, we can gather how many strawberries there are. That seems like a logical conclusion, but we'll explore that a little bit later. So we'll let p equal the number of plants. Okay, well, how are we going to compute the number of plants? We see a relationship here. 4 strawberry plants per square foot. So if we know the amount of square feet, we can get the amount of plants. So we'll let f be equal to the number of square feet. Okay, and we're also given the dimensions of this garden, 6 feet by 8 feet. Well, we can obtain the amount of square feet by computing the area of this rectangle. So how do we know that we need the area? Well, this comes down to basically analyzing the units. If f is the number of square feet, this has units feet squared, right? They're 100 feet squared in some sort of area. And this unit is obtained by multiplying 2 dimensions that have units feet. So, for example, in this garden, if we take the area of it by multiplying the length and the width, we get some number, in this case 6 times 8, 48, and its unit is feet squared. So the garden has area 48 feet squared. So area of garden equals 6 times 8, which is equal to 48 feet squared. So that means that f equals 48. Cool. So now we should analyze some of the other information given here and relate the other variables. So per square foot, let's just draw a little like box here representing 1 square foot, Carrie can plant 4 strawberry plants. So I'll just write the number 4 plants. And then within each of those plants, there's an average of 10 strawberries per plant. Okay, so what exactly does that mean? First, let's deal with the number 4. So the amount of plants, P, is related to the number of square feet because for each square foot, there are 4 plants. So we should multiply F by 4 to get the amount of plants, right? That makes sense. If there's 1 square foot, we expect to have 4 plants. 2 square feet, we expect to have 8 plants. I hope that siren isn't audible, but I'm afraid it is. Okay, so that's our first equation. Then we have perhaps another equation to create. She harvests an average of 10 strawberries per plant. So what does that mean? We have to be a little careful here because this says an average of 10 strawberries per plant. This doesn't necessarily mean that every plant has 10 strawberries, though if every plant did have 10 strawberries, then she would expect to harvest an average of 10 strawberries per plant, but the amount of strawberries per plant could differ. It's just on average. So what does average mean? The average number of strawberries per plant would be equal to the total number of strawberries divided by the total number of plants. This is just coming from the definition of average, where average means you take the total amount of things and divide it by how many other things there are. I guess that's bad wording, but in this case, if we're looking at the average number of strawberries per plant, it's sort of given in the wording here. This is a little hint. If you see strawberries per plant, the thing that comes before the per will be in the numerator, the thing that comes after the per will be in the denominator. So for example, the average miles per hour, you would take the total number of miles divided by the total number of hours. That's how we sort of create this equation. Okay, well on the left-hand side, we know that the average number of strawberries per plant, that's equal to 10, that's given. The total number of strawberries, we gave that the variable s, so this will be s on the numerator. And the total number of plants we gave as the variable p, so that'll be in the denominator. And I don't really like working with fractions, so we'll multiply both sides by p. Let me just write that here, times p, and we get 10p equals s. Okay, so we have 2 equations now. We have p equals 4f, and we have 10p equals s. And remember up here, we solved that f equals 48. And what are we trying to solve for? We are trying to solve for s. This is our target variable. And it seems like we have enough information to do this because s depends on the value of p, but p depends on the value of f, and we know what f is. So let's solve for p. So we have p equals 4 times 48, and you can multiply this out. You should get 192. And now we can say that, okay, s equals 10p, so s equals 10 times 192, which is equal to 1920, and that will be our answer. Because remember, s is the number of strawberries she expects to harvest, and that's what we're asked for in the problem. So our answer will be D. Nice. So again, this problem kind of similar to the first question we did, defining our variables for these unknown quantities and using what's given in the question to create these equations that relate the variables. Nice. Okay, so now for this question, we're given 3 hexagons of increasing size that are shown below. Suppose the dot pattern continues so that each successive hexagon, meaning the next hexagon, the one that comes next in the pattern, contains one more band of dots. How many dots are in the next hexagon? So first, what does it mean by a band of dots? Well, they sort of give it to us in the drawings, right? So in the first hexagon, we have just one dot, and it's a dark colored dot. In the next hexagon, we find that dark colored dot here, and it's surrounded by these light color dots, which creates a band. And the same thing happens in the next one, right? This is our original hexagon from the previous hexagon. And then we create this new dark color band around it. So that's what it means by band. And we're asked how many dots are in the next hexagon. So there's a couple of ways of doing this. I'll show you two different methods of how to solve this. And you can see which one you like better and perhaps use that in the future. But the first thing I would do is sort of like see if I can create some sort of pattern by how many dots are in each hexagon already, and see if I can use that pattern to compute the next value. Though I wouldn't always encourage doing that, especially when you'll only have 3 values in your pattern, because that's just such a small starting quantity to deal with that there could be many different patterns with the same 3 first values. But let's just do it anyways. So the first hexagon has 1 dot, the second one has 7 in it, and this third one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it has 19 in it. And looking at that, I don't really see an immediate pattern off of it, so I just will kind of not worry about that idea. So then it's like, okay, maybe we can generate this new hexagon. Just try to draw it, perhaps. And we can do that really easily because we know how to create the next hexagon. We just have to create a new band around this hexagon right here. So let's do that. I'll just erase some of this. Remember that there's 19 in this hexagon. And then we have to figure out how to create this band. So going from this hexagon to this one, let's take a look at what happened. So that hexagon, I'll just like draw the outline of it here, and we can see what went on. So in between these 2 dots, in the middle and right above it, we drew a new dot. And same thing goes here. We drew a dot in the middle above them and all the way around. And then, so that created these dots here. And then to create the hexagon, we sort of added these corner dots. So let's see if we can do something similar. So in between these 2 dots, I'll draw a new dot above them, in between them. Same thing here. And then again here, and so on. So I'll just quickly do this, and we'll see what happens. Okay, so we almost have a hexagon. We sort of have to add in the corner dots, which were like these dots here. So we'll do that. We'll draw a corner dot here, 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 there, and there. And that looks like a pretty convincing hexagon, right? Whoa, 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 whoa. If I do something like this, 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 there, I mean, like, that looks like it works. That looks like the next hexagon. So to figure out how many dots are in it, we can just take the 19 we started with and add on these dots that we just drew in. So how many new dots did we add? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 dots. So we started with 19, we added 18, so there are 37 dots in this next hexagon. So that will be our answer. And I'll show you a different way of solving this. Maybe you'll like it a little bit better. But I'm going to actually delete some of what I drew here, just so it's a little bit cleaner. So one way of doing this is considering how we computed these values here, like 1, 7, 19. Like, sure, we just counted them by hand, but maybe there's a smarter way of counting it. So here there's just 1, so we just say 1. But with the 7 here, we'll see that there's 2 dots in this row, but there are also 2 dots in the bottom row. And then there's sort of 3 in the middle. So we can say that like 7 was equal to 2 plus 3 plus 2. Okay? What if we look at this hexagon here? There's 3 in the top row, 3 in the bottom row, 4 in this second row, and 4 in this fourth row. And then we have 1 row of 5. So we said 19 is equal to 3 plus 4 plus 5 plus 4 plus 3. So we're sort of taking each row and like doubling it because we know it repeats somewhere below it. It's like reflecting across this middle line. So we can try to figure out a way of like creating a new summation for this next iteration. And it kind of depends on this middle value here that doesn't repeat. So in this case, the middle value was 5, here it was 3, here it was 1 in a sense. So we expect the next one to perhaps be 7. And then how many rows came above that, the middle row? So here, this is the middle row, there's 2 rows above it. Here, there's just 1 row above it. Here, there's 0. So here, when there was 1 row above it, we only had 1 value on either side. Here, where there's 2 rows above it, we have 2 values on either side. So we expect the next one to probably have 3 rows above it. And so 3 values on either side. And notice how each time the value decrements by 1. Right, we go from 5 to 4, 4 to 3, or alternatively 3 to 4, 4 to 5, until we reach that middle row. So the row right above the middle row should have 6 dots, and then 5 dots, and then 4 dots, and we only need 3 rows above it. And then we'll duplicate that for the bottom side, and so that should be our summation. And if we sum this up, we'll indeed get 37. So a slightly different way of solving it, but it's kind of identical to what we just did. It's just counting it in a different way. Instead of just by hand, 1 by 1, we're sort of grouping it by rows. So just a couple of different approaches for this problem. Nice. Let's move on to the next question. 3/4 of a pitcher is filled with pineapple juice. Wow, we dealt with lemon juice, now pineapple juice. The pitcher is emptied by pouring an equal amount of juice into 5 cups, into each of 5 cups. What percent of the total capacity of the pitcher did each cup receive? So, let's see. This is kind of similar to the money problem where we're dividing some quantity into so that each thing gets an equal amount. In this case, it's cups, before it was people. So a similar idea, we need to figure out, well, let's just say that like, let's create a variable because we're asked to find what percent of the total capacity of the pitcher did each cup receive. So since that's an unknown quantity, we'll create a variable. So let x be the percent capacity of the pitcher that each cup receives. So this gets x, this gets x, 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 right? Because they're all an equal amount. And this is how much pineapple juice there is, right? We can't have more than that. Like, we're given that it's 3/4 filled. The pitcher is 3/4 filled with pineapple juice. So 3/4 is nice, but that's a fraction, and we want percentage. So maybe let's just change that into a percent, just so we're dealing with, the same things. We don't want to be mixing percents and fractions. That could be confusing. So 3/4 is equal to 75%. So we'll say this is 75% filled with pineapple juice. And so this pineapple juice here gets distributed into all of these cups. So that means the total amount of pineapple juice in these cups should be equal to the total amount of pineapple juice that we started with, which in this case was 75% of the pitcher's capacity. And remember, each of these x is a percent. It's the percent capacity of the pitcher that each cup receives. So that means we can create an equation. X plus x plus x plus x plus x. The sum of those percentages should equal the percent capacity of the pitcher of pineapple juice that we started with. So we can solve for this. 5x equals 75. X equals 15, just by dividing by 5 on both sides. So that'll be our answer. So before I go on to the next question, just a couple of things. Sometimes it's a little bit daunting to be working with like summing percentages, and it just doesn't feel natural because we're so used to summing like numbers and decimals. So a couple of things you can do. First, you could change everything to be in decimals, and it'll be a similar logic, though again, we're summing values that aren't really like numbers, like numeric quantities of anything. We're doing percentages of something, so it still feels a little bit unnatural. So something else I sometimes like to do, usually to check my work, is to just provide a value. Let's say that like the pitcher can only hold like 100 liters. That's the capacity of the pitcher. If the pitcher is 3/4 filled with pineapple juice, then 3/4 of 100 liters is 75 liters of pineapple juice. I call it PA juice. And then again, we want to split this 75 liters into 5 cups. We can divide that number by 5, we get 15. So we'll get each cup 15 liters in each cup. And then we need to figure out what percent of the total capacity of the pitcher does each cup receive. Each cup is 15 liters. The capacity of the pitcher is 100 liters. 15 divided by 100 is 0.15, 15%. So exactly the same thing, we just decided to give an arbitrary value for the pitcher. And it doesn't matter which value you choose to start with. It'll work out to be the same 15% every single time, and that's just because of these variables here. We're just pre-assigning those variables. So I chose 100 because I know dealing with percentages, working with the number 100 is really nice, but you could do whatever and it'll still work. Maybe just require some more mathematics here and there. That's that question. Let's move on. Question 6. So Aaron, Darren, Karen, Marin, and Sharon rode on a small train that has 5 cars that seat 1 person each. Marin sat in... what? Is Marin a name? I guess it is. Okay. Marin sat in the last car. Aaron sat directly behind Sharon. Darren sat in one of the cars in front of Aaron, and at least one person sat between Karen and Darren. Who sat in the middle car? Okay, cool. So we have a train here. They're linked by cars, and we'll say that the train is going this way. I like to indicate the direction of the train because we mentioned something about someone being in the last car, so with a direction we know which one is the last car. So instead of calling them Aaron, Darren, Karen, Marin, Sharon, whoever, like, oh my gosh, so annoying, we'll just use the first letter of their names, ADKMS. So, Marin sat in the last car. Let's just put Marin here, because we know that happened. Aaron sat directly behind Sharon. So that means that there's no space in between Aaron and Sharon. Like, if Sharon sat here, Aaron must have sat there. And remember, this is going to be behind because the train is going in this direction. And, similarly, we could have SA, but we cannot have, like, S blank blank A, because that's not directly behind. Okay, but we don't really know where they sat. We can hypothesize, like, we can say, maybe Sharon sat here, so that means Aaron must sit here. We could also have Sharon sitting here, and then Aaron would be forced to sit there, or Sharon here, Aaron there. But we can't have Sharon here, because this spot is already taken by Marin. So those are sort of our 3 options. Darren sat in one of the cars in front of Aaron. So let's deal with that next. We don't know where Aaron sat, but we have 3 cases. So let's just deal with those 3 cases and see what we can gather. So in this first case, where Sharon is here, Aaron is here, Darren can't sit in front of Aaron because the only seat in front of Aaron is this car, which we already said Sharon occupies. So we know that this case just can't happen whatsoever. So we can just cross this out. Let's check this case here. So we put Sharon here, we put Aaron here. Darren sat in one of the cars in front of Aaron. So we can have Darren here because this spot is now unoccupied. We only took up these two seats. So this is also a possibility. What about this case here? We can have Sharon here, Aaron here, and again, Darren can go in either of these two and it would still work because Darren is in one of the cars in front of Aaron. So we haven't placed anyone really, but with this additional piece of information about Darren, we've eliminated one of the possibilities. So now we think about the last thing. At least one person sat between Karen and Darren. So let's think about it. Let's just try drawing it in. So let's consider this case first. We'll just put Sharon here, Aaron here, temporarily. Darren must have sat in one of the cars in front of Aaron, so this is the only available seat for him. And that leaves this fourth car for Karen, and indeed there is at least one person between Karen and Darren. So this configuration would work. Cool. Let's try the other case, where Sharon is here and Aaron is here. Well, we know Darren is in one of these two spots, so let's say we put Darren here, then Karen has to be there, but now there's not at least one person sat between Karen and Darren, right? They're right next to each other. And similarly, if we put Darren in the second car, then Karen would be here, and we have an issue once again. So none of these configurations work. So that means this is the only case which works, and we're asked to find who sat in the middle car. That would be Aaron. That's it. I don't really have much to say about this question. Just try to use some strategy. Don't be afraid of casework, sort of breaking it up into these three cases. And if you aren't able to immediately place people all of the time, like when we learned that Darren sat in one of the cars in front of Aaron, we weren't able to place any new additional people that we knew for certain. We were just able to eliminate some cases. So that's okay, and just, work from there. So that's that problem. All right. So this next question asks how many integers between 2020 and 2400 have 4 distinct digits arranged in increasing order. Okay, distinct digits is important. Let's highlight that. Distinct means different. So for example, 2247 would not be a valid case for this number, for these numbers, because there's 2 instances of the number 2. It repeats itself, so the digits are not distinct. We see that in 2357 in our example, all of the numbers are different from each other, so that works. And they must also be in increasing order. So with questions like this, where we're dealing with numbers and digits, what I like to do is sort of just draw some spaces here. And I drew 4 spaces because there's 4 digits in these numbers. And then sort of learn, or try to make some conclusions about what we know. If the integers are between 2020 and 2400, we know the first digit has to be a 2. It can't be a 1 because that would be less than 2020. It can't be a 3 or greater because that would be greater than 2400. So the first digit has to be a 2. The second digit is either 0, 1, 2, 3, or potentially a 4, right? And in this case, when the second digit is a 4, the only case is 2400. Like, we can't have 2, 4, something, something, because that would be greater than 2400. And this just doesn't work for what we're counting because the digits aren't distinct, they're not in increasing order, so we can just eliminate this case. Okay, let's consider when 0 is the second digit. Well, then we can fill in these 2 digits however we want, but they're not going to contribute to our total of the numbers that have digits in increasing order, because 0 is not greater than 2. So already we run into an issue here. So the case where it's 2, 0, blank, blank, contributes 0 numbers to our overall count. So that case is taken care of. Let's consider when we put a 1 here. Same issue. We can't construct any increasing digit sequences because 1 is not greater than 2. So again, if we have 2, 1, blank, blank, we have 0. Okay, let's consider when we put a 2 here. Same thing, except now for 2 reasons. It's not increasing, and the digits aren't distinct. We have a copy of 2 in there. So that just doesn't work at all. So 2, 2, blank, blank, contributes 0 as well. So that just leaves us with, we have to put a 3 here now. Okay, so now the last 2 digits. That's where it can be a little bit tricky. So the third digit could be well, how many digits are there left to work with? And I say left because we don't have all 9 digits to choose from, because we have to have distinct digits. So we can't have a 2 or 3 in the third or fourth digit. So we can choose 0, 1, 4, 5, 6, 7, 8, 9. But really, we can eliminate 0 and 1 because then they won't, it's not increasing because 1 is less than 3, 0 is less than 3. So we'll eliminate those, and we're left with 4, 5, 6, 7, 8 for this position. And the last digit depends on the digit that comes right before it. For example, I can't say that, then the value 6 could go in the last place, because what if we choose 8 for the third digit's place? Then 6 does not always work here. But if instead we chose 4 for this third digit, then 6 would work. So for that, we can do some case work, right? Let's consider the case where the third digit is 4. Then the fourth digit can be one of 5. It could be 5, like 2, 3, 4, 5. It could be 6, 2, 3, 4, 6, 7, 8, or 9, because we preserve the distinct digits and increasing sequence of digits. So that would be 5 total numbers. 2, 3, 4, 5, 2, 3, 4, 6, 2, 3, 4, 7, 2, 3, 4, 8, 2, 3, 4, 9. Okay, now we'll consider the case where the third digit is 5. The fourth digit, it can't be 5 again, because that would not be distinct digits. So it could be 6, could be 7, could be 8, could be 9. So there's 4 options here. Do another case here, when the third digit is 6. And then there's 7, 8, 9, so 3 choices. When the third digit is 7, the fourth digit can only be 8 or 9, so there's 2 choices here. When the third digit is 8, the fourth digit can only be 9. And when the third digit is 9, then the fourth digit can't be anything, because there's nothing greater than 9 that's a digit. Right, we can't choose 0, because 0 is not greater than 9, can't choose anything else, so this would be no options. So we can sum up these values here to get the total amount of values that work, because we just directly counted them. So 1 plus 2 plus 3 plus 4 plus 5 equals 15, and that's our answer. Now, I'll quickly mention something, that there's a much quicker way of doing all of this. It's a very, very quick thing to do, but it's a little bit of an advanced technique. And so what I mean by that is we have to be, a little bit creative with what we do. With these 2 digits, we concluded that they can't be 0 or 1, because then we don't have increasing thing. And they can't be 2 or 3, because then it wouldn't be distinct digits. So we know that both of those digits come from the set 4, 5, 6, 7, 8, 9. And what we can do is, since those 2 digits have to be distinct, just suppose I chose 2 random values from this set. In this case, suppose I chose 9 and then 5. I have these two values, 9 and 5. And I say that those are two digits that will create a number that works. We can't do 2, 3, 9, 5 because that doesn't work with the increasing thing. So we can only do 2, 3, 5, 9. And that works. It's a number in between 2020 and 2400 that has distinct digits, and they're arranged in increasing order. So let's try it again. Choose two other values. Maybe 4, 7. And again, that works, but 7, 4 doesn't work. So it seems that if we take two different numbers from the set and arrange them such that, like, let's call them x and y, and let's say x is less than y, then 2, 3, xy creates a number that works. So to count the amount of ways we can choose two distinct digits from this set, we do something called like a combination or choosing, where we say that there are 6 elements and we're choosing 2 of them. So this notation might be a little bit unnatural, so if you're not used to this notation, totally okay, something that you can learn. But this is saying from 6 distinct elements, we are choosing 2 of them, two distinct elements within them. And there's a little formula that we can use to compute what this is equal to. And this is equal to 6 factorial divided by 4 factorial to a factorial. If you don't know what factorials are, that's totally okay. It basically is saying that like 4 factorial is equal to 4 times 3 times 2 times 1. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. So you take the number, you multiply it by every integer less than it. And if you compute this, you'll actually get 15, which is exactly what we calculated here. But again, this technique is a little bit more advanced, so don't worry about it if this doesn't make any sense to you. Perhaps the idea makes a little bit of sense, where we take this set of potential digits that we could use and we're choosing 2 distinct values from there. The actual computations isn't something to worry about, but it's something you can look into if you're curious about it. Just something I wanted to mention. So yeah, that is this problem. A nice little digit problem. Let's move on to question 8. Ricardo has 2020 coins, some of which are pennies, and the rest of which are nickels. He has at least 1 penny and at least 1 nickel. Let's highlight that. What's the difference in cents between the greatest possible and the least possible amounts of money that Ricardo can have? So we somehow need to compute the amount of money that Ricardo can have. So let's try to do that. Let's create some variables. You know, we have an unknown amount of pennies, we have an unknown amount of nickels, and you know, somehow they create money, right? So we'll let P equal the number of pennies. And we'll let N equal the number of nickels. So how do we compute how much money he has just off of these quantities? Suppose he had 2 pennies and 3 nickels. Well, we can count this by hand, basically. Each nickel contributes 5 cents. So 5 cents, 10 cents, 15 cents. He only has 3 nickels. And then each penny contributes 1 cent. So we started with 15. This would be 16, 17. Okay, what if he had 4 nickels and 1 penny? We could do a similar thing, right? So here's 4 fingers for the nickels, 5, 10, 15, 20, and then 1 finger for the penny, 21. Cool. What if he had 847 nickels and 126 pennies? Well, that's not good. I don't have 847 nickels, and if I did, you would know about that. So what's going on here? When we're counting on our fingers by 5s, you know, we did 5, 10, 15, that's the same thing as doing 3 times 5. 3 times 5 is 15. Same thing with 4. 5, 10, 15, 20. 4 times 5 is 20, right? That's how multiplication works. And then we added to that the same thing, but what we did for pennies, right? 2 is the same thing, or we did 1, 2. That's the same thing as doing 2 times 1. Same thing, 1 times 1. So in essence, we can say that, okay, maybe this will be 847 times 5, and we'll add to that 126 times 1. So in case you're curious, what is this, 4235, and then we add to that 126, so that would be what, 4361? I don't know, just for fun. But the idea is that you multiply by 5, you multiply by 1, and add. So let m be the total amount of money. Then m should be equal to 1 times p. For each penny, it contributes 1 cent. And we add to that 5 times n. For each nickel, it contributes 5 cents. And we're adding those two quantities. So this is how we can calculate the amount of money, and we can test it by some of these values we put in. So if we put in 2 for p, 3 for n, we get 1 times 2 is 2, 5 times 3 is 15, 2 plus 15 equals 17, which is what we expected when we counted it earlier. Same thing, 1 times 1 plus 5 times 4 equals 21. Good. Okay. Now we need to find the greatest possible amount of money he could have, and the least amount of money that Ricardo could have. Okay, well, we know that nickels are more valuable than pennies. So if we want more money, we want a lot of nickels, because they're worth 5 cents. So let's consider what happens when he has as many nickels as possible. Well, how many nickels is that? Well, there's 20 possible coins. He has to have at least 1 penny. So let's just give him 1 penny so he's happy. And then everything else will be nickels. So let's consider the case when there's 1 penny and 2019 nickels. Okay? Because in this case, we have 2020 total coins. We've just maximized the number of nickels. Then the amount of money he has is 1 times 1 plus 5 times 2019. That's equal to 1 plus 10,095, which is equal to 10,096. Okay, maybe that's the greatest amount of money he could have. We don't know. But let's consider something else. So if he has X amount of pennies, then he must have 2020 minus X nickels, right? Because there's only 20 possible coins that he has. So let's consider, here we had 1 and 2019. What happens when we make the 1 penny 2 pennies? Then we decrement the amount of nickels. He should have 2018 nickels. And then he could also have 3 pennies and 2017 nickels. And it sort of is this balancing thing where we increase one by one and then decrease one by the other. So let's just see what happens if our calculation here is incorrect, meaning that this is not the maximum amount of money you could have. Let's just see what happens when we consider the case 2 pennies and 2018 nickels. Then m is equal to 1 times 2 plus 5 times 2018. That's equal to 2 plus 10,090, which is equal to 10,092. So we went down by 4 cents. This should make sense. Sense? It should make sense because we are removing 1 nickel. Right, from 2019 to 2018, we're removing 1 nickel. We're losing 5 cents, but in return, we're adding a penny. We're gaining 1 cent back. So each time we do this thing where we increment the amount of pennies by 1 and decrement the amount of nickels by 1, we're going to lose 4 cents. So even if we choose like 172 pennies and, 152, 1848 nickels, I hope that's right. We know for certain that this will be less than 10,096 because we just kept on adding pennies, right, to get up to 172, and then we kept on losing nickels to get to 1848, and we're losing 4 cents each time, so it's going to be less. So this is indeed the greatest amount of money you could have. So what would be the least amount of money he has? That's when he has the most amount of pennies, right? Like when we continue increasing the amount of pennies until we can't increase it anymore. So that'll be when there's 2019 pennies and 1 nickel. And we have to have 1 nickel because it tells us that he has at least 1 nickel. So let's compute M. M equals 1 times 2019 plus 5 times 1. That's equal to 2019 plus 5. That's equal to 2024. And so this will be the least amount of money you could have. And we're asked to find the difference in cents between these two amounts. So we'll just take the difference. 10096 minus 2024 is equal to 8072. And hopefully that's an answer choice. Yes, it is. That is our answer, choice C. Good. So just another problem with creating variables, creating equations, things like that. Yeah, when it comes to maximization and minimization things, you just want to sort of like consider the extreme cases. That's what we did here. We considered the extreme case where we had the most amount of nickels, and the other extreme where we had the least amount of nickels or the most amount of pennies. That's how we approach these problems. Let's move on to question 9. Akash's birthday cake is in the form of a 4 by 4 by 4 inch cube. The cake has icing on the top and the 4 side faces, but no icing on the bottom. Suppose the cake is cut into 64 smaller cubes, each measuring 1 by 1 by 1 inch as shown below. How many of the small pieces will have icing on exactly 2 sides? This, I mean, it's kind of math, but it's not as mathy as some of the other questions. We just have to be a little bit, we have to put a little bit of thought into what we're counting. So let's just draw some icing on here, right? We have some icing here, have some here, and on the other sides, like on here and on the back, but nothing on the bottom. So we need to see which pieces have icing on exactly 2 sides. So let's consider this corner piece right here. That has icing on 3 sides, right? It has it here, here, and here. The other 3 sides of the cube, because it's a cube, as said here, and cubes have 6 sides, the other 3 sides are on the interior of this cake, so they don't receive any icing. So in this case, this corner piece will have 3 sides with icing, so we don't count it. Same thing for this corner piece here, this corner piece, and that corner piece. So those corner pieces are not going to contribute to our total because they have icing on 3 sides. But if we look at this edge piece here, that will have icing on only 2 sides, right? This side and this side. The other 4 sides are on the interior. So this would be a good one. So this is a good one. Same thing with this edge piece. And in fact, all of these edge pieces on the top layer will work. So that's good. We also have to consider these center pieces. But they only have 1 face exposed on the exterior, so they're only going to get 1 thing of icing, so that just won't work. So we've sort of covered this top layer here. Let's consider the last few layers here. Same issue with the center pieces. They only have 1 side with icing on them, so that's just not going to work. These edge pieces still work. They receive 2 sides. I don't really know how to explain it very well, but it's sort of just like breaking it apart into considering edge pieces, center pieces, corner pieces. Same thing with this edge piece, in the back here, and then there's 2 on the far back side. Yeah. On like the back edge, which is not visible. I'll try to, like the edge that goes here, right? The cube looks something like that in the back. And we're talking about this edge here, like these 2 edges. So there's 2 back there as well. Now we just have to consider this final layer here. And at this point we're in the mindset that, okay, if we find an edge, we're good because it has 2 sides, but we have to be careful because the bottom face does not have any icing on it. So for example, this edge piece will only have 1 side of icing on it. because 4 of the sides are on the interior and the one on the bottom doesn't receive icing. So that doesn't work. And then the center pieces at the very bottom, those have no icing at all because the only exposed face doesn't get any icing on it. And then there are the corners, and we're tempted to think that, oh yeah, corners had 3 sides, not good. But in this case, we'll take a look at this corner piece, for example. This side has icing, that side has icing, and we expect the bottom side to have icing, but it doesn't. So that corner only has 2 sides with icing, which is good. So we have to account for this corner in our total. Same with this corner, the one in the back, and the one that's hidden. So now we just count how many things we counted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So in this case, our answer should be 20. So, I mean, it's not really mathy, it's just being, a little careful because I totally would have missed these corner pieces the first time around. Like, I would have completely forgotten about them. So, it's good to be a little bit careful. Okay, so move on to question 10. Zara, I don't know, has a collection of 4 marbles. An Aggie, a Bumblebee, a Steely, and a Tiger. She wants to display them in a row on a shelf, but does not want to put the Steely and the Tiger next to one another. How many ways can she do this? So we can draw a little shelf here, and then there's 4 spots for these 4, whatever they're called, marbles. And we have this constraint that the Steely and the Tiger can't go next to each other. Okay. So, there's a couple of things we can do. We can brute force this out, and perhaps that's doable because from the answer choices we know that the maximum possible answer is 24, so that seems doable. Or we can use some little advanced counting techniques. Let's see. First observation. The total number of arrangements, without any constraints, is equal to number of arrangements with the Steely and the Tiger next to each other plus the number of arrangements without the Steely and Tiger next to each other, right? Either the Steely and Tiger are next to each other or they're not, and the total amount of arrangements is the total amount of arrangements within each of those subcategories summed together. And we can sum them together because those cases are disjoint, meaning that there's nothing that overlaps in those 2 categories. We're not double counting anything. And that comes from the fact that we're casing on whether or not Steely and Tiger are next to each other or not. Okay. How many total arrangements are there? We have 4 distinct items. So let's try to fill in our spaces. We have 4 options for the first item. It could be any of the 4 items that we put in the first spot on the shelf. Once we put that item, we can't use it again. So in the second spot, there's only 3 items left to place. So there's 3 options for the second place. Now we've used 2 of our items, there's only 2 left, so the third spot only has 2 options, and the last one is whatever's left over. So if we multiply this all together, we get 24 total ways to arrange the items. That's kind of a good sign because our answer at max is 24. If this value was 12 or something, then we could eliminate these 2 options because that exceeds the total amount of possible arrangements. But in this case, we can't really make any conclusions because we don't have any answer choice greater than 24. Okay, so let me just erase some of this. So this is 24. And now we're trying to solve for, she does not want to put them, so we're trying to solve for this quantity here. There's 2 ways we can do it. Either we can count that quantity directly, or we can count this quantity and then solve for this by subtracting this on both sides, right? If this is, like, let's call this x, and we'll call this y, then we can solve for y by doing 24 minus x. Either way works. So let's try to do it. Let's try to solve for this. Why not? And the way we're going to do this is we have 4 spots. And we're going to force the S and T to be next to each other. I forgot what the others are called. So there's A, B, S, T. We're going to force them to be next to each other. So let's consider S and T as a grouping. We'll just group them together and we'll place them right next to each other. So what I mean by that is let's first fix like the grouping to take up these 2 spots here. So S and T are in that grouping, they definitely will be next to each other. So we can have S here, T here, or we can have T here, S here. Either way it works, they're right next to each other. And then we have A and B left, so we could have AB and BA, right? And this works for both cases. We could have STAB, STBA, or TSAB, TSBA. So here there's 4 options. And the way we get this is, like 4 is equal to 2 times 2. This 2 comes from the amount of ways we can arrange the S and the T within the grouping. And this 2 comes from how many ways we can arrange the A and the B. Essentially, 2 options for this spot, and then 1 option for this spot. Okay, so that's a good start. Let me erase some of this. Now we have to consider what happens if we put the grouping here. Well, then there's 2 ways to arrange the S and the T within that grouping, either ST or TS. And then for this spot here, we can either put an A or a B. So there's 2 options. And here, whatever is left, either the A or the B, which we didn't use. So there's 1 option here. 2 times 2 is again 4. So we get another 4. And now we consider the last case where the grouping is at the end. And again, 2 ways to arrange the S and the T. Here, it can be either an A or a B, 2 choices. Here, there's only 1 thing left, 1. Multiply them together, we get another 4. So we get 4 plus 4 plus 4 equals 12 cases where the S and the T are next to each other. And we can add them because they're disjoint, because we cased on where the S and the T grouping was. So there's no overlap between our cases. So that means x equals 12. So we have 24 equals x plus y, which means that 24 equals 12 plus y. Therefore, y equals 12. And that will be our answer. So you could also solve for this directly, also by doing casework. It would be a very similar thing where now we do we have the 4 spots, and then maybe we would put S here, and then we don't want T next to it, so we would consider when T goes here, and then arrange the A and the B, so there's 2 options. In this case, you could also say that, okay, what if we put T at the very end? And again, there's 2 cases. And then you have to consider the case that, okay, what if we put T here and S here? And then all of these sorts of cases of arranging the S and the T such that they're not next to each other, you'll still get 12 as the answer. Just a couple of ways of approaching that. So yeah, that's question 10. Okay, so unfortunately I lost a lot of the recording, so I have to redo some of this, but this should not disrupt from your viewing experience. So I think we're now on problem 11, which is a graph question, so let's read through it. After school, Maya and Naomi headed to the beach 6 miles away. Maya decided to bike, while Naomi took a bus. The graph below shows their journeys, indicating the time and distance traveled. What was the difference in miles per hour between Naomi's and Maya's average speeds? So we're dealing with average speeds here. So it's very important to know, first, what does speed mean, and then second, what does average mean? So when we think about speed, we're already provided the units. we're provided the units for average speed, but it's also the units for speed being miles per hour. So, if you drive a car, you're used to, or if you know someone who drives a car, you're used to seeing things in miles per hour, maybe kilometers per hour. So that's a measure of speed. And again, we're seeing the word per, and there's a helpful hint that we're probably going to have to divide two quantities. The thing that comes before the per is in the numerator, the thing that comes after the per is in the denominator. So we expect speed to be some sort of fraction of miles divided by hours. And another way of writing this is okay, we're considering how many miles are traveled. That's another way of saying that is the distance traveled. And hours are a unit of time, so we can just say distance divided by time. We just need to make sure that the units are correct in miles and hours respectively. Okay, now we have to talk about the average speed. So when we're considering the average speed, it's for an entire journey, right? We're computing their average speeds for the entire journey that they took. So we don't really care what happened in between the journey, we just want to look at the journey as a whole. So we're looking at the total distance that's traveled in the journey and the total amount of time that it took. So we would say the average speed is equal to the total distance divided by the total time. Cool. So now we have an equation to find average speed. Now we can find Naomi's and Maya's average speed and then take the difference. So we'll start with Naomi's average speed. So for this, we need the total distance that she traveled as well as the total time. So Naomi's journey is indicated by this dotted line. And we're looking at the entire journey. So we want to essentially look at the end point of her journey. We don't want to really consider any point in between her journey because there's still things that occurred afterwards as well as before it. If we look at the end point of her journey, then we've encapsulated everything that occurred before it. So we'll be taking a look at this point up here to gain some insight into her, the total distance traveled and the total time. So if we trace along our grid to get to that point, we see that this is at the 6 mile mark, which is good because the journey, we're told, is 6 miles. The beach is 6 miles away. And downwards, we're told that it took her 10 minutes to reach the 6th mile. So we'll use those two data points in our quotient. So the total distance is 6 miles, and the total time is 10 minutes. Good, so we can compute this, and we get 0.6. However, we need to specify units. What are the units? In this case, it's miles per minute, which is not good, because the question asks for miles per hour. So we sort of have to change some things around. So one thing we can do is change the minutes in the denominator to hours. So we need to figure out how many hours is 10 minutes. Well, we know that 60 minutes equals 1 hour. And we're saying that 10 minutes is going to be equal to some amount of hours, we'll call it x. So what we can do is multiply the bottom equation on both sides by 6, and we get 60 minutes is equal to 6x hours. Well, we know that 60 minutes is 1 hour, so we'll use these two results that we got to get 6x is equal to 1, or x equals 1/6 of an hour. So 10 minutes is equal to 1/6 of an hour. So now we can return to our quotient here. We'll use 6 miles in the numerator. Now we'll use 1/6 of an hour in the denominator. And when you divide this, you'll get 36, and your units will be miles per hour. Good, so that's Naomi's average speed. Now we need to figure out Maya's average speed. And we'll do a very similar thing. Maya's average speed. So we need the total distance that Maya traveled as well as the total amount of time it took her. So going back to the graph, again we'll look at the final point of her journey, which is this top right corner. And indeed, if we trace over, we get, we're at the 6 mile marker, which is good because the beach is 6 miles away. And if we trace downwards, we see that it took her 30 minutes. So we'll do the same thing. 6 miles goes in the numerator. 30 minutes goes in the denominator. We have to change these minutes to hours, so you can do a similar exercise where you create some equations and then solve for x, or you can just realize that 60 minutes is 1 hour, 30 is half of 60, so 30 minutes is 1/2 of an hour. So this would be equal to 6 miles divided by 1/2 of an hour, which is equal to 12 miles per hour. Great. And remember, the question was asking us to find the difference between their average speeds. So we have both of their individual average speeds. Now we just have to take the difference. So 36 minus 12 is going to be equal to 24 miles per hour. And that is answer choice E. So the main takeaway from this question is make sure you're comfortable with reading graphs. Just know which point you're looking at. In this case, it was the end point of the journeys. And usually the x-axis and y-axis will give you good information about that point. So just trace over in both directions to the side and downwards, just like I did, to get some information there. Also very important to be comfortable with averages and knowing what average means, how to compute average quantities. In this case, we did average speed. And I think in a different problem, we did something else with average. So yeah, important concepts to be aware of. Let's move on to question 12. Question 12 says, for positive integer n, the factorial notation, we talked about this earlier, n factorial represents the product of the integers from n to 1. So for example, 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. What value of n satisfies the following equation? And we're given an equation. So there's a couple of ways of approaching this. Maybe you're tempted to compute the left-hand side, multiply that out, and then divide by 12, so that way we isolate n factorial, and then find n that way. Totally fine. The only issue is that some of these numbers are going to be annoying to work with because factorials grow really, really quickly. For example, 5 factorial is just 120, but 9 factorial is 362,880. So your first step would have to be first computing these factorials, and then you have to multiply these two numbers together, 362,880 times 120, which just seems like a lot of work. Or another thing that could be helpful is maybe once you compute these factorials, you notice that, 120 and 12 appear on opposite sides. Maybe there's some sort of cancellation there that you could do. That works too. And in fact, that'll get you the correct answer pretty quickly if you make one sort of realization. But here's the realization that I'll make. Notice how factorials are defined. We're given 6 factorial, for example. So 6 factorial we're given is 6 times 5 times 4 times 3 times 2 times 1. Let's write out a different factorial, maybe 5 factorial. So that would be 5 times 4 times 3 times 2 times 1. Do we notice anything immediate? Maybe not. If not, that's okay. What happens if I take what I just wrote and shift it over? Now hopefully you're seeing something. The difference between 6 factorial and 5 factorial is this 6. The 5s are aligned in a sense. Same with the 4s, 3s, 2s, and 1s. So really, if I throw in some parentheses around here, we see that 6 factorial is equal to 6 times 5 factorial. This is just a helpful thing to be familiar with. These are just rules of factorials. But yeah, that's a really neat trick that, okay, we can move downwards in a sense. We can express 6 factorial in terms of a smaller factorial. And sure enough, 5 factorial can be written as 5 times 4 factorial. And you can work the other way. 7 factorial is going to be equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's going to be 7 times 6 factorial. So we can always represent these factorials in terms of other smaller factorials. Okay, so with that in mind, let's work on the problem. The left-hand side seems to be the one that will require the most work. And that's the side we should work with since the n is on the other side. And we want to eventually isolate that or work with that. So let's work with the left-hand side. 5 factorial times 9 factorial. I'm just going to expand them out. We are given the factorial definition, like multiplying these numbers. So let's just apply that to 5 and 9 and see what happens. So 5 factorial times 9 factorial is going to be equal to 5 times 4 times 3 times 2 times 1 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. Okay. So now, like I said, we could divide this left-hand side by 12. That would totally work. So yeah, we can do that. The issue is now we're like, okay, how do we divide by 12, right? We can see some factors of 12 in here. For example, here's a 4 and there's a 3 that multiply together to be 12. But there's also a 2 and a 6, right? So, I mean, we could cancel any pair of these, but maybe one is better than the other. Who knows? Because we're going to have to do some more multiplication. So another way of doing this is to just form a 12 with what we have. So it's basically the same thing, but choosing 2 factors, making a 12, and then leaving everything else. So for example, let's take this 4 and this 3 out. So we'll say that this is equal to 4 times 3 times 5 times 2 times 1 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it's just sort of rearranging these terms in a friendly way. And you might be asking, why didn't I choose the 6 and the 2? For a couple reasons. One, the way I'm doing it will make it a bit easier. And second, we were just seeing that factorials can be built off of other factorials. So if we're trying to build an n factorial, maybe we can build it off of either the 9 factorial or the 5 factorial, right? So I want to preserve one of these factorials, in this case 9 factorial, to maybe act as one of these terms here, and then perhaps create like a 10 factorial or an 8 factorial. And indeed, when you simplify these 2 terms here, we get 12, which is what we want, because there's a 12 right here, times 10 times the 9 times 8 times 7 times 6 thing, right? And look at that. This is very similar to what we were just doing over here as our exercise, right? This is 10 times 9 factorial, which would be 10 factorial. So this is 12 times 10 factorial, which means n is going to be equal to 10. So, I mean, like I said, we extracted a 4 and a 3 out here. I said it was because it would be easier, and it was easier. You could have also extracted a 4 and a 3 out from here to make the 12, and then what would have happened is this 4 and 3 would have substituted in for this place to reconstruct the 9 factorial, and you would still be left with 5, 2, and 1. You could also have chosen the 6 and the 2, but that would also destroy the 9 factorial, but you could recreate the 9 factorial by using this 3 and 2 as a 6, and then the other 2 will come as a factor from this 4. So then you would be left with 5 times 2, which would be 10, and then you would have your 9 factorial. I'm sort of verbally explaining this instead of writing it out. So if you want to try doing it that method, by all means go ahead, you'll get the correct answer. And if you struggle, just rewind and listen to what I just talked about, and hopefully that'll guide you along the right path. But yeah, for this, factorials, super important to know these sort of definitions on the left. They're not really definitions, but just know how you can construct factorials off of smaller factorials, things like that. Cool, let's move onwards. Question 13. Jamal has a drawer containing 6 green socks, 18 purple socks, and 12 orange socks. After adding more purple socks, Jamal noticed that there is now a 60% chance that a sock randomly selected from the drawer is purple. How many purple socks did Jamal add? Okay. So I think maybe the most confusing part of this question is the line about there's now a 60% chance that a sock randomly selected from the drawer is purple. What does that mean? Let's say he had 100 socks and 50 of them were purple. Would we say that there's a 60% chance that a randomly selected sock from the drawer is purple? No, because there's only 50 socks. And each sock is essentially equally likely to be drawn out from this drawer. You know, he's not more likely to draw an orange sock than a green sock. If you were just given like 3 socks, a green sock, a purple sock, and an orange sock, one of them is not more likely to be drawn out than the other one. Like, they're all identical socks, it's just the color that's different. So what I'm saying is, if we have 50 socks out of 100, there's not a 60% chance that he'll select a purple one. It would be a 50% chance. So that means we would expect 60% of the socks in the drawer to be purple. So that's what we should be targeting. So in fact, let's start by creating some variables so we can express what we want in terms of these variables. We want, out of all of the total socks, 60% of them to be purple. So let's use some variables. So first, let's let P equal the total number of purple socks after he adds socks. So let P equal total number purple socks after adding. Okay, that's good, right? That should be 60% of the total amount of socks. So let's create a variable for the total number of socks. So we'll let n be the total number of socks after adding. And remember, we're asked to find how many purple socks did Jamal add. This is an unknown quantity to us right now, so perhaps let's create a variable for it. We'll let x equal the number of purple socks that Jamal added. Okay. So now we can create some equations, right? We wanted 60% of the total socks to be purple. So that means if we take the total number of purple socks and divide it by the total amount of socks, we should get 60%. Or alternatively, 0.60. And notice I'm using P and N because these are the amount of socks, or these are the socks after he adds the socks, which is when we have that 60% chance. Cool. So we have an equation, but we're solving for x, and our equation doesn't have x. So let's try to put x into this equation. Let's take a look at the letter P, the total number of purple socks after adding some. We know that he starts out with 18 purple socks. And then he adds some more. In fact, he adds x socks, x purple socks to the 18, and that results in P socks, because P is the amount of purple socks after he adds them. So we can say that P is equal to the 18 he started with plus the x that he added. Cool, so we can substitute that in. But we can also do something for n, right? We know how many socks there were originally. We know how many socks he added, being x. He didn't add any other colors, so he only added x more. So that means the sum of these 3 values is how much he started with, plus x more will give us n, the total amount of socks after he's done adding socks. So n will be equal to 6 plus 18 plus 12 plus x, which is going to be 36 plus x. So now we can substitute back into our equation, and we get 18 plus x divided by 36 plus x is equal to 0.60. I don't really like working with decimals just because multiplying integers with decimals can be challenging for me. And subtracting and adding decimals is not my cup of tea. So I'll convert this into a fraction, 6 over 10 or 3 over 5, whatever you want. Now we just have an equation with one variable, and the way we can solve this is do some cross multiplication. So we multiply these two together and set that equal to the product of those two. It's the same thing as multiplying the denominator on both sides. So this will give us 10 times 18 plus x equals 6 times 36 plus x. Distribute, we get 180 plus 10x equals 216 plus 6x. You can move the x terms to the left side and the integer terms to the right side and get 4x equals 36, x equals 9. And that's how many socks he added, 9. And you can check your work, right? You can check that, okay, he has 36 total socks to begin with. Let's say he adds 9 more, so there's 45 socks in the end. How many purple socks are there in the end? 18 plus 9 is 27. And so 27 divided by 45 is going to be 0.60. So it is the correct answer. There we go. Main takeaway from this question is know your percentages, be able to change it to fractions, and remember to always create variables. Even if you don't need to use them, it's better to define them than not to define them. Cool. Next question. Question 14, another graph question. There are 20 cities in the county of Newton. Their populations are shown in the bar chart below. The average population of all the cities is indicated by the horizontal dashed line. Which of the following is closest to the total population of all the 20 cities? Okay, so we're looking for the total population. And so there's a couple ways of doing this. Suppose I didn't give you the graph. Suppose you were just given the names of the cities and their populations, and I asked for the total population. Well, how do you compute that? You would just take all of the individual populations and add them together, right? That's just what total population means. It's the sum of the individual populations. So we can do that here. And that would work. Maybe. The reason why I say maybe is because there are 20 cities, which is a lot of cities to deal with. And these are pretty big numbers, so it's very easy to make a mistake. But the main reason why it's not the best way to go is that some of these bars lie in between the tick marks. So you're going to have to do some estimation of what that value actually is, because you can't say for certain. So with those intermediate roundings and you have to trace over correctly, it's a recipe for disaster in most cases. Okay, so how else can you solve this? Well, they gave us something. They gave us this dotted line. It would be really bizarre if that was given for no reason, right? Why would you give us that? So surely it must be used in this problem, and in fact we will use it. So first we need to figure out what is this line. We're told that it's the average population of all the cities. So again, we're dealing with averages. So what does average mean? Average population, it's basically the total amount of something divided by the total amount of something else. So in this case, we have cities and population, which is people, right? Measured in people. So those are the two things we'll probably divide. So do we divide population by cities or cities by population? In this case, we're going to do the total population divided by the total amount of cities. right? So why is it not the other way around? Well, if you think about it in the current form, the units will be people in the numerator divided by cities, so it'll be 1 million people per city, for example, which is good for population, right? That's a logical unit. If it was the other way, then it would be like 20 cities per person, which doesn't make sense when we're talking about population. So we're taking the total population divided by the total number of cities. Okay, well, we're looking for the total population that's in the numerator. So if we know the average population and the total amount of cities, then we're good, right? The total population is going to be equal to the average population times the total number of cities. Okay, that seems doable, right? Because we're given a line for average population and we're given the total number of cities, right? Total number of cities is 20. They tell us that. How do we find the average population? For that, we're going to have to look at our dotted line and see where it touches this y-axis that indicates population. So let's zoom in to here. We'll make the assumption that these tick marks are equally spaced, meaning that when we go up from 4,000 to the next tick mark, that's an equal amount increase as going from that tick mark to the next tick mark. Since we don't know how much we're going up by in between consecutive tick marks, let's give it a variable name. So the next tick mark will be 4,000 plus x. Sure. The next one will be 4,000 plus x, where we are, plus another x. So that would be 4,000 plus x, or alternatively we can just say plus 2x. Next one will be, you guessed it, 4,000 plus 3x. And the one where it says 6,000, that's given to us, but we can also say that that's equal to 4,000 plus 4x. Right? It's just adding that extra x amount from the previous one. So now we can solve for this x value, this mysterious x value, by solving this equation. So let's do it off to the side. 4,000 plus 4x equals 6,000. Subtract 4,000 on both sides, you get 4x equals 2,000. So x equals 500. So let's return to where we had these tick marks with x. Let's just substitute in our value for x. We said it's 500. So the first tick mark will now be 4,500. The next one will be another 500 on top of that, which would make it 5,000. And then another 500 on that will make it 5,500. Our dotted line appears somewhere in between this 4,500 and 5,000, and it appears to be in the exact middle, or very, very close to it. So, how do we find the middle of two numbers? We need to find the average of these two numbers. For example, 1 and 3. The average of these two numbers is 1 plus 3, which is 4, divided by 2, since there's only two numbers we're working with, which is 2. And 2 is the middle of 1 and 3. Again, you can do the middle of 3 and 7. Take their average. 3 plus 7 is 10, divided by 2, since there's two numbers, 3 and 7, we get 5. And 5 is the middle of 3 and 7. So we need the average of 4,500 and 5,000. To do that, we'll just find the average like I've been saying. So we'll do 4,500 plus 5,000 divided by 2. That's going to be 9,500 divided by 2. And you can divide that out, get 4,750. So this dotted line is pointing to 4,750. And that's what we'll say the average population is. So if we go back to our work here, we'll substitute 4,750 for the average population. And now we can multiply. 0, 0, 0, 5, 9, 95,000. And that should be our answer. Sure enough, that's answer choice D. So that's what we'll go with. Takeaways from this question. Number 1, be comfortable with averages. We've seen this pop up so many times. It's going to show up, so know your averages, know what it means. Second, be comfortable with reading your graphs and tracing over to the axes, just like we saw in the other problem. And third, the middle of two numbers, in this case 4,500 and 5,000, is equal to the average of the two values. Hopefully those takeaways are helpful. Let's move on to question 15. All right, so this one says, suppose 15% of x equals 20% of y. What percentage of x is y? I remember when I learned about percentages many years back, and some tricks to be aware of. So the main thing that I always remember is whenever I see the word of, I'm prompted to do multiplication. What does that mean? Let's say I have $100. What is 15% of my $100? Maybe you're just saying, oh, that's just $15, right? It's pretty obvious. Yeah, you're right. What if I had $120? What's 15% of that? Well, that's a little bit harder to compute. And in fact, the way that you'll compute it is by taking the product of 15% with 120. You mentally did that when I said I had $100. You took 15% and multiplied that by 100. 15% is the same thing as 0.15. So if you do 0.15 times 100, you get 15. So you would do the same thing with 120. You would do 0.15 times 120, that would get you 18. So $18 would be 15% of 120. Notice how I'm saying of all the time. 15% of 100, 15% of 120. That prompts for multiplication. So if 15% of x equals 20% of y, that means that 0.15 times x, 15% of x, equals 0.20 times y. The question literally writes the equation for us. We just had to know that of meant multiplication. So we already have an equation. We're asked to find what percentage of x is y. So we need to say like, oh, 20% of x is y, or 20% of x equals y, right? So that means we're going to have some sort of equality relationship between y and x, but we're going to say like 30% of x is y, 40% of x is y, which is very similar to the wording here. So that means we need to multiply x by something, some percentage, which we'll call z, and that should equal y. So we need to find this mysterious z value. Well, how are we going to do that? We see an x and a y on opposite sides of this equal sign, which is what we have here. And here we have y isolated. So why don't we isolate y in this other equation by dividing by 0.20 on both sides? So we get 0.15 divided by 0.20x equals y. And if you divide that out, 0.15 divided by 0.20, you'll get 0.75x equals y. Wait a second, that's exactly what we're looking for, right? If we read this out loud as a percent now, this would say 75% of, since we're multiplying, x is y, right? It reads out for us. 75% of x is y. That's exactly what we're looking for here. So this 0.75 aligns with this z, which is what we're looking for. Our answer, 75. Main takeaway from this question, when you see percentages and the word of, you should be thinking about multiplication. Don't forget to change your percentages to decimals. That's how we do math with percentages. But yeah, those are the tips from this question. Cool. All right, so now we're at question 16, which looks like a geometry question. Each of the points A, B, C, D, E, F in the figure below represents a different digit from 1 to 6. Each of the 5 lines shown passes through some of these points. The digits along each line are able to produce 5 sums, one for each line. The total of the 5 sums is 47. What is the digit represented by B? What does this mean? Okay, this is a very strange question. Each of the 5 lines shown passes through some of the points. Yeah, I buy that. This line, for example, passes through A, B, and C. The digits along each line are added to produce 5 sums, one for each line. Okay, so what that's saying is, suppose we take this line ABC. We take the digits on that line, which in this case are A, B, C, because we're told each letter represents a digit, and we sum them together, A plus B plus C, and that forms a sum. We don't know what it's equal to. I'll just say it's equal to question mark. But that's one sum. And then we can take another sum. So let's take this line, for example. That passes through B and F. So B plus F equals some other question mark. And we can do this for all 5 lines. So let's do that. There's also C plus D plus E equals question mark. There's A plus F plus E equals question mark. And there's B plus D equals question mark. So these are the 5 sums that were mentioned in the problem, one for each line. We're told the total of these 5 sums is 47. So what does it mean by total? That means if we take all of these sums, combine them together into one supermassive sum, that will be equal to 47. So in essence, the sum of these question marks is equal to 47. Okay, well then why don't we add all of these together and set it equal to 47? It's a lot of terms, but hopefully it'll put us on the right path. So I'll scroll down a little bit. And so we'll get A plus B plus C plus B plus F plus C plus D plus E plus A plus F plus E plus B plus D is going to be equal to the sum of our question marks. But we know that that sum is equal to 47. Okay? For the left-hand side, let's group the like terms. We see a couple of A's, so we can make that 2A, just to simplify things a little bit. So we get 2A plus 3B plus 2C plus 2D plus 2E plus 2F, and that all equals 47. So we see a lot of these 2A, 2C, 2D, 2E, 2F, but we don't have 2B. We can create a 2B by splitting 3B into 2B plus B, so why don't we do that? I mean, we don't have a good reason to do at the moment, but there's so many 2's, maybe it's a good idea to. And what happens when we see a lot of 2's or a lot of the same coefficients? Well, that means we can factor it out. So let's factor out a 2 from all of the terms that have a 2 coefficient. So that'll be equal to 2 times A plus B plus C plus D plus E plus F. And then we also have to tag along that extra B from the 3B. That equals 47. Okay, so it seems like we've done a lot of math, but I don't know how much progress we've made. Remember, we're solving for B, the digit that B represents. So, how are we going to go about doing this? What we need to notice is that even though we don't know what each letter represents, for example, F could be 4, or it could be 2, I don't know. But we need to notice that we can actually solve this sum very easily. Why is that? There are 6 letters that we have, and each one represents a different digit from 1 to 6. That means each digit is going to be used exactly once, and each for a different letter. So we don't know how to split these up or how to assign them, but we do know that the sum of A through F is going to be equal to the sum of 1 through 6, because each number will show up exactly one time in this assignment, and since a plus b plus d equals like a plus d plus b. We can rearrange our sum however we want, and we'll see that like we'll get that this sum, a plus b plus c plus d plus e plus f, is going to be equal to this sum 1 through 6. Hopefully that makes sense. If not, I encourage you to pause, take a moment to convince yourself why that's true. But much of the reasoning of why it's true is because there's 6 letters, six distinct digits, and there's a 1-to-1 correspondence between these assignments. So no number will repeat in its assignment. So that means we can simplify this sum to be 2 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. This is not to say that A equals 1 and B equals 2 and C equals 3. That may not be true, and in fact it's not true in this question at all. We're just saying that we can somehow rearrange these terms within it such that the assignment will correlate with 1 through 6. That's what I'm getting at. Again, we still have to add b because we don't know what it is, and in fact that's what we're solving for. And we say this equals 47. You can sum up the terms inside of the parentheses. That sums to 21 plus b equals 47. This means 42 plus b equals 47. And indeed, b equals 5. That will be our answer choice E. Okay, so this didn't actually end up being a geometry question. It was more of an algebra question. But what's the main takeaway from here? Honestly, I wouldn't really call it a takeaway. It's more of just being creative and making this observation of the 1-to-1 correspondence between these, and knowing that we can solve for this sum just with the information we have. Maybe another takeaway is seeing that when we did this thing here and grouped like terms, we saw a lot of 2 coefficients, and we wanted to create one more with the b. That would be something to be aware of. But yeah, that's that question. On to question 17. How many factors of 2020 have more than 3 factors? So as an example, 12 has 6 factors, namely 1, 2, 3, 4, 6, 12. And is 12 a factor of 2020? Wait, is it 1282? I don't think it is. Okay, I guess that's just telling us that the number 12 has more than 3 factors. So yeah, good to know. So how are we going to solve this? There's a couple of ways of doing it. The first way that I think many people may be tempted to do, which I will actually do for you, is to just factorize 2020, list out all of its factors, and go from there. So let's do that. Let's see. 1 divides 2020. I know that. So does 2, because the number's even. 3, it doesn't. You can like check, you can divide through it, or just know by your divisibility rules. And we can keep on going. The next one will be 4, the next one will be 5, 10, and I'll just list them out at this point. But you can already see that finding these factors may take a really long time. You just have to you go through all of them and then hope that you reach every single one of them. Right? So we've listed out all of the factors, and hopefully we've reached all of them. Maybe we haven't, maybe we skipped some. So already that's the issue with this approach. But now we would go through each of these factors and see how many have more than 3 factors. So 1 has 1 factor, just 1. 2 is prime, so it has 2 factors, 1 and 2. 4 has 3 factors, 1, 2, and 4. 5 is prime, it has 2 factors, 1 and 5. 10, you can list out its factors. It'll be 1, 2, 5, 10. There are 4 of these, and you just keep on doing these and listing them out, and I'll just list them out here. And I'm not spending too much time on this approach because honestly I don't really like it too much, and there's a very high possibility of making errors. Like, how do you know for sure 505 has 4 factors? How do you know you didn't miscount? But basically from here you would see that, okay, now I'll just check mark the ones that have more than 3 factors. I missed one? Oh wait, sorry. 10, 10 should be 8. Sorry. Yeah, and then you'll see that, okay, there's 7 factors with more than 3 factors. That's one way of doing it. As you can tell, I'm not too enthusiastic about it. So let me show you a different way of approaching this problem. So we can say that the total number of factors of 2020 is going to be equal to the number of factors with more than 3 factors, which is what we're looking for, added with the number of factors with less than or equal to 3 factors, right? Because either its factor has less than or 3 factors or more than 3 factors. It falls into one of these categories, they're disjoint, so when we add them together, we'll get the total number of factors. Because for something to fall into one of these categories, it must also be a factor of the number, so we are indeed counting the total number of factors. This is basically saying like an analogous situation would be saying the total number of integers, the total number of positive integers less than or equal to 10 is equal to the total number of integers less than or equal to 5 plus the total number of integers in between 5 and 10. Something like that, where you're just partitioning it into 2. Okay, very complex wording on my part. We're solving for this highlighted part. So, the first method I showed was the direct way of counting it, but we can also solve for this by finding the total number of factors and then subtracting the amount of factors with less than or equal to 3 factors, which may be easier. But first, how do we find the total number of factors of the number? We can do what we did here and list them all out and hope that we got everything. But there's another trick which I really, really want to teach you because it is super, super helpful in all sorts of math competitions especially. So let's look into it. What we're going to do is take the number 2020 and we want to prime factorize it, which means we want to write it as the product of a bunch of prime numbers. So we need to split it apart into the product of prime numbers. So for example, I'll start with 2 and then see if 2 goes into 2020. If not, then I'll move up to 3, then I'll move on to 5, 7, and I'll just move upwards through the primes until I have the product of prime numbers. Let's do it and you'll see what I'm talking about. So I know 2 divides 2020 because 2 times 1010 is equal to 2020. Okay, now let's try to decompose 1010. We know that that's divisible by 2 as well. You might also be like, oh, it's also divisible by 10. Like I see that right there. You're right, but 10 is not prime. It's still much higher than 2. And remember, we're going to build our way higher and higher. So we'll say that this is equal to 2 times 2 times 505. Okay, 505 is not divisible by 2, so we can move away from 2. Let's check the next prime, 3. Is 505 divisible by 3? No. So we move to the next prime, which is 5, which it is divisible by. So we say this is 2 times 2 times 5 times 101. And then we look at 101. Is that divisible by 5? No. 7? No. And you keep on going and you'll realize that 101 is actually prime. So we've done it. We've expressed 2020 as the product of a bunch of primes. Now we're going to combine like primes and use power notation instead. So we can say that this is equal to 2 squared times 5 times 101. And in fact, what I'll do is instead of just saying times 5, I'll say 5 to the power of 1 and 101 to the power of 1. The reason why I'm doing this is because to find the total number of factors of the number, we need these powers. So it's easier to just see a 1 than just nothing there. So the way we compute the total number of factors of 2020 is what we're going to do is we're going to increment each power by 1 and multiply together all of the powers, all of the new powers. So let's zoom in here and see what I'm talking about. So we have 2 squared. The power is 2. we're going to increment it by 1, so that becomes 3. We move on to the next power, which is 1, 5 to the power of 1. We're going to increment it by 1, it becomes a 2, and keep it as is. Look at the next power, 1, increment it by 1, that becomes a 2. And now we're going to multiply all of these new powers together. 3 times 2 times 2 equals 12. And indeed, if you look back into what we just did up here, we listed out 12 factors. So 2020 has 12 factors. This is how you compute the number of factors of a number. Works for any number, just a helpful trick for you to know. Cool, so we've already solved for this part. Now we just have to find the number of factors of 2020 with less than or equal to 3 factors. And for this we can do casework. We consider the case with exactly 1 factor, exactly 2 factors, and exactly 3 factors, and sum those all together. So let's do that. Case 1. Number of factors with exactly 1 factor. And notice that we're not starting at 0 factors because there aren't any numbers with 0 factors. Okay, so which numbers have exactly 1 factor? The only number with exactly 1 factor is 1. And indeed, 1 is a factor of 2020, so this case contributes 1 value to our total. Nice. Case 2. Number of factors with exactly 2 factors. So what kind of numbers have exactly 2 factors? These would be prime numbers. This is something you should memorize and be very familiar with. Prime numbers have only 2 factors. So these would be prime numbers. So how many prime factors does 2020 have? Well, we can look at our prime factorization. We've written it out as a product of primes. So the numbers that we see here, the bases, those are going to be the only primes that divide 2020. So in this case, there are 3 values that contribute to this case. Pretty cool. Case 3, the number of factors with exactly 3 factors. So this one might be a little bit more tricky, but there's a couple things you need to know. First of all, a number will have an odd amount of factors only if it's a square number. So there's no other number which will have an odd number of factors. It has to be a square for it to have an odd number of factors. I'll give a very, very brief explanation of why that's the case. It's not going to be very satisfactory, but maybe this will help. Why, if you don't believe me? Up here, when we listed out the factors of 2020, we've listed out pairs of factors in a sense. 20 is paired with 101 because their product forms 2020. 10 is paired with 202 because their product forms 2020. 5 with 404, 4 with 505, 2 with 1010, 1 with 2020. So we're forming these pairs, so we would expect there to be an even number of factors because for each one factor there's an associated other one. With perfect squares, we have some number in the middle because that middle number is the square root of that number. So for example, if you list out the factors of 64, there's going to be an 8 right in the middle. And right before that 8 will be a 4, and to the left of the 8 will be a 16. So it'll be 4, 8, 16. The 4 pairs with the 16, the 8 pairs with itself. 8 times 8 is 64. This is the very brief, not a very rigorous proof, but it's important to know that square numbers have an odd number of factors. So that's just odd number of factors. We're looking at specifically 3 factors. And this only occurs when we're dealing with a square of a prime number. I won't really explain why this is true because I don't want to make it more confusing than it already is. But maybe like try to draw it out, list out the factors and see why that's the case. So we need the square of a prime. If we look at our prime factorization, we see, hey, there's a prime and it's squared. And if we look at all of the other primes, they don't have another term to be multiplied with, so we can't find another square in there. So this 2 squared equal to 4 is the only one that contributes, so we have one thing in this case, for a total of 5 factors with less than or equal to 3 factors. So if we come back to our equation up here, we can solve for the blue highlighted region because we know the total number of factors is 12. I'll just say that this is equal to x. And we said the total number of factors with less than or equal to 3 factors is 5, x equals 7, which is what we got above. So the first method was quicker, I guess, maybe, because I expedited the process quite a bit. And the second one felt a little bit longer, but with the first one you have to be super careful in making sure you're getting all of the factors, and then you have to go through all of those factors and then find their factors, like lots of work. Second option, still a lot of work, but it's a little bit cleaner to work with. The main thing I want you to take away from this problem is this trick here of finding the number of factors of a number. This comes up so often, it's very, very helpful to know. So that would be this question. Let's move on to question 18, which actually looks like a geometry question. The last one kind of baited us, but rectangle ABCD is inscribed in a semicircle with diameter FE, as shown in the figure. Let DA equals 16, and let FD equals A equals 9. What is the area of ABCD? Okay, so we know ABCD is a rectangle. The area is going to be equal to length times width. We already know one of these dimensions, right? We know that AD equals 16. So if we find AB or DC, we're in business. Okay, so we have a semicircle, which is basically a circle, but too shy to become a normal circle. It's just half of it. I don't know. But we're given that it has diameter FE. Okay, what is the length of the diameter? So what is FE equal to? Well, FE is equal to FD plus DA plus AE, which is going to be 9 plus 16 plus 9, 34. Okay, good. Whenever I see diameters, I'm always thinking about its brother or its sister, which is the radius. And similarly, when I see a radius in a problem, I'm always thinking about its diameter. These two go hand in hand. They're so similar to each other. It's like, why not just have them both? So let's think about the radius. The length of the radius is going to be half the diameter. So that means the length of radius is going to be 1/2 of 34, which is 17. That might be helpful. But first, we have to find a radius in this circle. Remember that the radius connects the center of the circle to a point on the edge of the circle. We don't really have a center of a circle in this drawing, so why don't we just draw one right here, and we'll call it O. So if the length of the radius is 17, we can solve for OA and OD, because we know that OE equals OA plus AE. We know that OE is going to be 17 because that's the radius. And we know that AE equals 9, so that means OA equals 8. So I'll cross this out, draw 8 here, and similarly OD will be equal to 8. Cool. So we have a center defined and we have some other dimensions. We're still looking for AB. How can we find AB? Well, now we really have to do something. It seems like we've used a lot of the information of the question, but we have to think, what else do we know? ABCD is a rectangle, so we weren't able to say too much about its side lengths. What about its angles? Well, all of the angles are right angles. So why don't we just draw that? Okay, and now maybe we're starting to see something. We're looking for AB or CD, right? And we have this OA, AE, and we're looking for this AB. In particular, this OA seems of interest. And if we draw these, let's see what happens when we connect O with B. That's a right triangle, right? If I highlight this, when I highlight it in blue, oh, it doesn't look like it. I'm not doing this correctly. All right, I didn't do a good job of it, but that's a right triangle, right? It has 3 sides and it has a right angle there. So maybe we can find AB that way, because we know some stuff about right triangles. In particular, the Pythagorean Theorem could be of use. So let's consider the Pythagorean Theorem. That says that OA squared plus AB squared equals OB squared, right? The sum of the squares of the legs of the right triangle equals the square of the hypotenuse of the right triangle. This is good because we're looking for AB and we know what OA is. Do we know what OB is? Yes, we do. What is OB? OB is this line that we just drew, but it's connecting O, which is the center of the circle, to B, which is on the edge of the circle. OB is a radius. It's a radius. Oh my gosh. We know the length of the radius. OB is going to be 17. We solved for the length of the radius. This is so exciting. That means we can solve for AB in here because we know this and we know that. So let's do it. OA squared is going to be 8 squared. We'll tack on AB squared. OB squared is 17 squared. Let's simplify this. 64 plus AB squared equals 289. AB squared equals 225. That means AB equals 15. Excellent. Now we know that this side length is 15. Remember, we're looking for the area of this rectangle. So area is equal to length times width, which is going to be 16 from this DA side times 15, 240. That's our answer. Main takeaway from this question: if you see circles, think radius and diameter, especially if they give you the diameter. Find the radius. And if you need to draw your center point in the circle, go for it. Just do it. And yeah, know what a radius is. Connects the center point to a point on the edge, because you can always draw in these extra radii and they can be super helpful. Sometimes if you're like really desperate and you can't figure out what to do, it may be helpful to just like draw random lines between some of the points that are given to you, because maybe you'll just stumble across this line, this realization of drawing OB. Like, making this right triangle may not have been immediately obvious, but if you're just like, doodling and you happen to stumble across OB, that could be something to do. Excellent. Let's move on to question 19. All right, on to problem 19. A number is called flippy if its digits alternate between 2 distinct digits. For example, 2020 and 37373 are flippy, but 3883 and 123 are not. How many 5-digit flippy numbers are divisible by 15? Okay, so first let's draw some spaces that we would like to fill in with digits to construct a 5-digit flippy number. Okay, so the digits alternate. So we can look at 37373, for example. So whatever the first digit is, that must be the same as the third digit and also the fifth digit, as we see here. There's a 3 in the first, third, and fifth digit. So in a sense, these positions are linked to each other. Then the second digit is going to be distinct from the first digit, and that's going to be the same as the fourth digit, right? This is just due to the alternation of the digits. So those two are linked. Cool. We want to construct 5-digit flippy numbers that are divisible by 15. And the reason why I say construct is because it would be super annoying to go through all 5-digit numbers, first determine if it's flippy, and then see if it's divisible by 15. That's just too much time, right? So the way that we'll do this is we'll try to construct these 5-digit flippy numbers, and that might be easier. So with that in mind, we have to think, when is a number divisible by 15? When is a number divisible by 15? Note that 15 is equal to 5 times 3. So if a number is divisible by 15, it has to also be divisible by 3 and divisible by 5. So we need the number to be divisible by 3 and divisible by 5. If we have these two things, then we're in business. We have a number that's divisible by 15. Okay, so when is a number divisible by 5? If I were to give you any random number, 27, is that divisible by 5? No, you can divide it through and see that it's not. What about 1,037,465? Again, you could also divide it and see that it works in this case. But the divisibility trick is to look at the units digit. If the units digit is a 5 or a 0, our number is divisible by 5. And we can see this by listing out the multiples of 5. 5, 10, 15, 20, 25, and so on. They all end with 5 or 0. So that means in our flippy numbers, we need the last digit to be a 5 or a 0. Okay? I'm just going to erase these lines, and what I'll do is just change the colors of the spaces. So the same color spaces are linked with each other. So we want the units digit to be a 5 or a 0. 5 or 0. Let's just say the units digit is a 0. Let's plop a 0 in there. Then we also have to fill in the spaces that are linked to that space, which is the third spot and the first spot. And let's just suppose we randomly fill in the other two spaces with a different digit. What's the issue? This number is not a 5-digit number anymore. It's a 4-digit number. We just put a 0 in front of it. So no matter what we do, we're always going to have that leading 0, which does not make it a 5-digit number. So that just means we can't have 0 in the units digit at all. We can put a 5 here, and then we don't run into that issue. Okay, so now we have to figure out the second digit. Like already we've reduced the problem so much, right? We know that the only possible flippy numbers divisible by 15 look like this. So what we can do from here is test every single other digit, go 0 through 9 in here, and fill them out, check if 50505 is divisible by 15, and then check if 51515 is divisible by 15, and count your way upwards. That's perfectly fine. There's only 10 things to check, not too bad. But we can also reduce that just a tiny bit more by using the other fact that we need the number to be divisible by 3. When is a number divisible by 3? If you're not familiar with divisibility tricks, I highly encourage you knowing them. Like for 5, we just looked at the units digit. There's a lot of other divisibility tricks. For example, for divisibility by 2, you look at the last digit, see if that's divisible by 2. For 4, you look at the last 2 digits. For 9, you have to add all the digits and see if the sum is a multiple of 9. So at least know your rules for like 1, 2, 3, 4, 5, 6, I guess 8 and 9. 8's not that bad. I skipped 7 because 7 is very annoying and it's just not worth it. But if you want to learn it, go ahead. Anyways, all that is to say, know your divisibility rules. So a number is divisible by 3 when the sum of its digits is divisible by 3. So for example, 27 is divisible by 3 because 2 plus 7 is 9. 9 is divisible by 3. So in this case, we have 3 of our digits. We're missing 2 of them. Let's just plop an x in those spots for now, where x will be some digit that we're looking for. The sum of these digits is 5 plus x plus 5 plus x plus 5. That's 15 plus 2x. And we want this number to be divisible by 3. We want it to be. So that means 15 plus 2x should be divisible by 3. Well, 15 is already divisible by 3, so we would want 2x to also be divisible by 3. That means the only values of x that work are 0, 3, 6, and 9. So these 4 digits will make the number divisible by 3. We also handled the case where it's divisible by 5, so it has both of these requirements. So all 4 of these, 50505, 53535, 56565, 59595, those will all be divisible by 15. You can double check just to make sure of your answer. There's only 4 things to try now, but indeed our answer will be 4. Main takeaway from this question, learn your divisibility rules if you don't know them already. 1 through 9, just not 7 if you don't feel like it. That's this problem. Let's move on to the next question. We're in the final stretch here, problem 20. A scientist walking through a forest recorded as integers the heights of 5 trees standing in a row. She observed that each tree was either twice as tall or half as tall as the one to the right. Unfortunately, some of her data was lost when rain fell on her notebook. Her notes are shown below with blanks indicating the missing numbers. Based on her observation, the scientist was able to reconstruct the lost data. What was the average height of the trees in meters? Okay. So, what does average height mean? Again, we're seeing average so much, so it's very important to know your averages and what they mean. So in this case, average is going to be the average height, and for that, we're going to need the total height divided by the number of trees. We know how many trees there are. We don't know the total height just yet because we're missing the heights of the trees. So we'll come back to that later. Let's try to see if we can figure out the heights of the trees. We know that each tree is half as tall or twice as tall to the tree, twice as tall as the tree to its right. So tree 2 is to the right of tree 1, and we know tree 2 is 11 meters tall. So, if tree 1 is half as tall as tree 2, then it would be 11 halves meters high, which would be 5.5. If tree 1 was twice as tall as tree 2, then it would be 22 meters high, 11 times 2. Both of these are viable options because we know that one of these two must hold. However, if we go back to the question, we see that the heights are integers. So if we come back here, we can eliminate this first option of 5.5 since that's not an integer. So we know tree 1 must be 22 meters high. Okay, we know tree 2, let's move on to tree 3. We don't have anything to the right to compare it to because tree 4 is to the right of tree 3. However, we have tree 2, and tree 3 is to the right of tree 2. So we can use that information. So tree 2 is either half as tall as tree 3 or twice as tall as tree 3. If tree 2 is half as tall as tree 3, then tree 3 must be 22 meters tall. The other option is if tree 2 is twice as tall as tree 3, then tree 3 would be 11 halves meter high. But we just said 11 halves can't happen since that's not an integer, so tree 3 must also be 22 meters. Now let's do tree 4. If tree 3 is half as tall as tree 4, then it could be 44 meters tall. And if it's twice as tall as tree 4, then tree 4 could be 11 meters tall. So we have two cases, both of which are possible in this case since they're both integers, so we don't know for sure. So now we need to find tree 5, and there's a couple of cases to consider based off of what tree 4 is. So let's say tree 4 is 44 meters high. If tree 4 is half as tall as tree 5, then tree 5 would be 88 meters tall. If it's twice as tall as tree 5, then it would be 22 meters tall. For 11, if tree 4 is half as tall as tree 5 would be 22. And if it was twice as tall as tree 5, then it would be 11 halves, but that just can't happen. So we have three cases to consider. Either it's 1122, 4422, or 4488. One of these three hopefully is the correct answer. How are we going to figure out which one is correct? Well, let's use the last piece of data we haven't used, the average height being blank 0.2. Let's call it x.2, because I don't like the blank. So if the average height is x.2, we can say that average height is x.2, which we can rewrite as x plus 0.2, since x is an integer. That's going to be the total height divided by the number of trees, which is 5. So the total height is going to be equal to 5 times x plus 0.2, which is equal to 5x plus 1. Remember, we don't know what x is, and actually we're trying to figure out what x is. But that doesn't matter too much. What we're given is that the total height is going to be one more than a multiple of 5, right? 5 times x, any number x, will produce a multiple of 5. So the total height needs to be one more than a multiple of 5. Okay, so then why don't we just take these three cases, find the total height for all of these three cases, and figure out which one has a total height which is one more than a multiple of 5. Let's try it. So, case 1. Maybe I'll zoom out a little bit just to see. So the total height here would be equal to 22 plus 11 plus 22 plus 11 plus 22. That's equal to 88, which is not one more than a multiple of 5. Okay, let's try case 2. Total height is going to be equal to the 22 plus 11 plus 22. The first three trees we know for certain, those are the heights. We've already argued that. Tree 4, in this case, we're letting it be 44, and then we're letting tree 5 be 22. If we sum this together, we get 121. Hey, that is one more than a multiple of 5, so that's looking promising. Let's look at case 3 just to be safe. So here the total height is going to be 22 plus 11 plus 22 plus 44 plus 88. What's this equal to? 187, which is not one more than a multiple of 5. So we've already just deduced which case we're working with, which is going to be the 4422. Great. We're asked to find the average height. We can compute this really easily now because average height is equal to the total height divided by the number of trees. Total height, we just said, was 121, and there's 5 total trees. Divide this out, we get 24.2, which is going to be answer choice B. What's the takeaway from this question? It's kind of this sort of realization here, that the total height is going to be one more than a multiple of 5. That's the big thing from this problem. And I guess it's just all about using all of the data that's presented to you. Maybe sometimes there will be extra data that you don't need, but whatever is given to you, use it, and hopefully that'll get you the right answer. Alright, let's move on to question 21. A game board consists of 64 squares that alternate in color between black and white. The figure below shows the square P in the bottom row and square Q in the top row. A marker is placed at P. A step consists of moving the marker onto one of the adjoining white squares in the row above. How many 7-step paths are there from P to Q? Okay, there's a couple ways of doing this, as there usually is for problems. Method 1 is to just try to trace out all of these paths. And we see that the answer will be somewhere in between 28 and 35, which is manageable to do by hand, but it can be a little tricky to make sure you didn't double count certain paths. The second option is to be a bit clever, which unfortunately is usually the harder method, but this is how you learn stuff, right? Okay, first thing to note, we're looking for 7-step paths. What's so special about 7? Well, Q is 7 steps, or 7 rows above P, right? We're 1, 2, 3, 4, 5, 6, 7 steps above Q. So that means we can't move downwards at any point. We have to just continue moving upwards. That helps us out a lot. So what we're going to try to do is draw a network of possible paths, or I might call them roads, that you could travel from. So for example, if I start at P, the next step, I can either follow this road or this road. Those are my only two options. And similarly, if we look at the end point from Q, the previous step can be either of these two roads, right? Now we sort of have to connect everything together, and we'll keep on creating these V-shaped type things. So I'll start from the top. So we can draw 2 more roads, and then for the right square, we can only draw 1 row since there isn't anything to the bottom right. Moving on to the next row, we draw 2 here, and then 2 here. For the next row, 2, 2, and just the 1. Now I'll start working from the bottom up just so like you can see that perspective. So this will have 2 roads coming out of it. This one will have 2 roads coming out of it. And note, I'm not moving further to the left because there wasn't anything reachable from P further to the left. And now we can sort of connect things together. And notice how there's no road like this either, just because that's not reachable from P. So this is our network, right? We know that our paths will follow these roads that are drawn. It's not going to follow anything up here, anything like that, because we've shown it's not possible. Okay, so now you could choose to draw the paths. I mean, that would also work. But again, we can be a bit clever. The way we're going to be clever is we're going to forget about P. We're just going to look at each of the white squares that we have and just pretend like we're solving the problem for that square. So for example, let's look at this square right here. We want to know how many ways are there to reach Q, and only by moving upwards, because we've already constrained our problem that we have to move upwards since it's a 7-step path. So if we're here, the only option we can choose is to move up and to the left. There's only one way to get to Q from this square. We can't move downwards. So let's draw a little 1 in this box. So what this means is, starting at this square, there's one way to get to Q. But alternatively, what it means is, suppose we reach this square from some other part, if we started further down, then there's only one way to get to Q if we reach this square. Okay, let's take a look at its neighboring square, which is this one. How many ways are there to get to Q from that square? Also just 1. You have to take the road up and to the right. So 1. Let's look at the next row. Let's look at this square. How many ways are there to get to Q? Well, I can count 1, And that's it. I can't go up and down again because I moved downwards, and that's just not good. So there's only this one path to get to Q. Another way of thinking about that is if I'm at this square, the only road I can take out of it is this diagonal one, which means we reach this square, and we've already determined there's only one way to get to Q from this square. So if we start here and there's only one choice of movement, and that square tells us there's one path to Q, that means there's only one path starting from this square. The reason I say that is because we'll use that logic for this square. Here we have two choices. If we go to the left, there's only one path to get to Q from this square. And if we go to the right, there's only one way to get to Q from that square. So in total, there are two ways to get to Q from this square, since we've cased on all possible directions of travel. So this will be a 2. All right, let's move to the next row, and we'll actually start with this square, and then we'll fill in everything, because hopefully we'll start to see a pattern. Again, from this square, we have two options. We can go left, and if we go left, from here, we know there's only one path to Q. If we go right, from this square, we know there's two paths to Q. So in total, there are 3 paths to Q from this square. And now you can sort of see that the blue number I'm writing in is the sum of its neighbors, or it's the sum of the squares connected to it in the row right above it. So for example, this square only has one neighbor in the row above it, so it's just going to take the sum of those values, which is just 1 in this case. Similarly, this square has only one number here, so that gets the number 2. All right, let's fill these in now. So hopefully you're starting to see the pattern. Here, its neighbors are 3 and 2, so their sum is 5. This square has neighbors 1 and 3, sum is 4. This square has neighbor 1, so it's just 1. And then we can fill in the rest. 5, 9, 5, 14, 14, 28. And remember what these blue numbers meant. The blue numbers told us how many paths to Q are there starting from the square I'm at. And we worked all the way down to P, and this says 28. There are 28 paths to Q starting from P. That's exactly what we're looking for in this problem. That's going to be our answer. This question is tough, I'm not gonna lie. Knowing how to do like this, breaking it apart into smaller things is very tough, and it's a skill that you have to build up. But yeah, the thing is, like, if something seems too difficult to count by hand or too tedious, try to break it down into smaller subproblems. In this case, the subproblems were counting the amount of paths just from any square in the grid to Q, and using that to build up all the way to P. So even though these cells in the middle, these squares, seem to be kind of pointless, we still wanted an associated value for each of those squares. So like I said, it can be tricky to build up that intuition, but with more practice, you'll get it. All right, on to problem 22. When a positive integer n is fed into a machine, the output is a number calculated according to the rules shown below. So if it's even, we halve it, and if it's odd, we do this 3n plus 1 thing to it. So we have an example. If n equals 7, well, you can read through it, but it's saying like, oh, it's odd, so we do 3 times 7 plus 1, 22. We feed it into the machine again, 22 is even, divided by 2, 11, so on, and we do it, we repeat that process 6 times, right? We're asked to find the sum of all values of n such that we reach 1 after the 6-step process. Okay, so a couple of options. We can work forwards, start from n and hope that we reach 1, or work backwards, start from 1, figure out what we could have previous to 1, and hopefully find what n is. I like the second option better because we're building up to the correct answer instead of trial and error. So, let's see. All right. I'll just rewrite the rule here. If n is even, it goes to n over 2. If it's odd, 3n plus 1. We get n. This is what we had, right? Okay, let's consider the step right before the last step, where we feed in some number and we get 1 in return. Well, let's suppose, we'll call this number like x, right? And we feed that into the machine. If x is even, then we have it and we get 1. So that means x could be equal to 2, right? Because 2 is even, half of 2 is 1, which is what we want. If x is odd, then we would have fed it into the machine, done 3n plus 1, and we would have said 3n plus 1 is equal to 1. Or sorry, 3x plus 1 equals 1. Well, if you solve for x, you get x equals 0. The issue is that 0 is not odd. So if we had x equals 0, we wouldn't have said do 3x plus 1, because 0 is not odd. So in fact, we can't run into this case, which means x has to be equal to 2. Cool. Now let's do the step right before it, and we'll call this thing x. If x is even, then we halved it to get 2, so 2 times 2 is 4, right? So if 4 is even, we do 4 divided by 2, we get 2. That's good. What happens if x is odd? Then we would say 3x plus 1 equals 2. If you solve for x, you get x equals 1/3. 1/3 is not an odd number. It's a fraction. So this case also can't happen, right? We can't have an odd number whose output will be 2. So that means this x must be 4. Okay, so we're in good shape. We're building up our way. Let's move on to the step right before that, and we'll call this x. So this could be 8, right? Because if x is 8, it's even. In the next step, we have it, so 8 divided by 2 is 4. That's good. Or we could have had 3x plus 1 equals 4. And if you solve for x, you get x equals 1. And that works. So if, for example, we put a 1 in for x, we would have to feed it into this line up here, because 1 is odd, and we would get 4 outputted. So both 1 and 8 in this middle spot would work. Okay. So I guess we can't determine this slot necessarily if we don't know what comes right after it. So why don't we case on whether or not it's 8 or 1. So case 1 will be that the middle spot is 1. So then we're left with n arrow blank, and then the rest we've already determined. Okay, well, let's take a look at this spot. This situation is identical to the situation here, where we had a blank arrow 1, and we deduced that this spot had to be a 2. Similarly, this spot must be a 2. And again, this situation right here is identical to that situation that we had up there, and we deduced that the spot right before the 2 must be a 4, so we can automatically fill in this spot to be a 4. And sure enough, this situation right here is identical to that situation there, so we conclude that n in this case could equal 1 or 8. So when the middle spot is a 1, we conclude that n is either 1 or 8. Pretty cool. Now we have to consider the second case. The middle spot is an 8. And then we have to redraw it. Okay, so now we have to actually calculate what this spot is. So again, we'll call it x. If x is even, then x over 2 equals 8, which means that this could be 16. If x is odd, then 3x plus 1 equals 8, which would mean that x equals 7/3, but 7/3 is not odd, so that case can't occur, so we know for sure that this spot must have a 16 occupying it. Alright, let's move to the next spot, put an x there. If x is even, then x over 2 equals 16, which means it could be 32. Or we could have 3x plus 1 equals 16, and then we would say that x equals 5. So we could have 32 or 5 in this case. 5 works because it's odd, and 3 times 5 plus 1 is 16. So again, we have to do some casing now, so we'll call this case A, where I'll just say x equals 32, and we're solving for n, which is the spot right before it. So if n is even, then n over 2 would be equal to 32, so n would equal 64, so n equals 64 works. And if n is odd, then we would have 3n plus 1 equal 32, but that would say that n is equal to 31 over 3, which is not an odd number, so that case can't occur. So when x equals 32 here, we have n equals 64. Case B is when x equals 5. Then if n is even, n divided by 2 will equal 5, which means n equals 10 works. And otherwise, we would have 3n plus 1 equal 5, but then we would have n equals 4/3, which is not odd, so that case can't occur either. So we've figured out all values of n. We have 1, 8, 64, and 10. The question asks for the sum of these values, so we just compute 1 plus 8 plus 64 plus 10, and we get 83. And sure enough, that's answer choice E. What's the takeaway from this question? Very similar to the previous question, where we worked backwards, right? So this is another common theme that we're seeing a lot. Working backwards is often more efficient than working forwards and guessing and checking our way there. So that's that. Let's move on to question 23. 5 different awards are to be given to 3 students. Each student will receive at least 1 award. In how many different ways can the awards be distributed? So let's call the awards A1, A2, A3, A4, A5, right? And they're all different from each other as designated by the numbers. And we'll call the students P, Q, and R. How can we easily describe a method of distribution of the awards? Well, for each award, we can specify who it was given to. So for example, let's say award 1 was given to student Q. Let's say award 2 was given to student R. Award 3 may be P. And let's say award 4 and 5 both went to Q. This combined together forms a string QRPQQ. So this string of 5 characters actually tells us how the awards were distributed. If I give you a different string, you can tell me how the awards were distributed. You would tell me that award 1 went to student R, award 2 went to student P. So we've modeled the situation as a simple string. This is something I really like to do when there seems to be some sort of complex situation. Try to reduce it down into something tangible, something that's easy to work with. Okay. We have a certain requirement that each student must receive at least 1 award. Okay? So that means there are some good strings, which each student will have at least 1 award, but there's also some bad strings. So the 2 that we wrote right here, QRPQQ and RPQQR, both of those are good because each student appears once, right? In this case, P gets award 3, Q gets a bunch of awards, and R gets award 2. So each one gets at least 1. Same thing with this one. An example of a bad string would be something like Q, Q, R, R, Q, because person P doesn't get any award. Similarly, P, 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 P would be bad because Q and R don't receive awards. And I realize the color scheme is not really good because the green strings are bad and the red strings are good, but my bad. So we want to count the number of strings such that we don't have any of these bad strings. First, how many strings are there? Well, the first award can be distributed to 3 possible students. So there's 3 options for this first character of the string. The second award can also be distributed to 3 possible students. So there's 3 options for the second place in the string. So 3 options for the first, 3 options for the second, and same for the other awards. And we'll multiply these together since the distribution of the awards are independent of each other. This gives us 3 to the 5, which is equal to 243 total strings. So this includes all of the good strings and all of the bad strings. Now, let's get rid of the bad strings. So let's try to get rid of the strings that look like this, where there's 1 person missing. So that means, in a sense, each award can be given to only 2 people, since we're forcing 1 student to not get any of the awards, right? So now A1 only has 2 people that they can give it to, since we're excluding 1 person. So there would be 2 options for A1. Similarly, 2 options for A2, and so on. 2 to the 5th, which is equal to 32 strings. So this is saying there's 32 strings of this form where we're excluding 1 person. We have to be a little bit careful though, because there are 3 people we could exclude, right? We could either exclude P, we could exclude Q, and we could exclude R. For each person that we exclude, there are 32 corresponding strings to it. So in total, we have to multiply this by 3 to get 96 strings. So then we would want to do 243 minus 96 to get our answer, but we have to be very careful. We have to be extremely careful, especially by how we did this by construction. So we haven't taken care of these PPPPP cases, right? Where 2 people don't get the awards, right? The issue is we've already counted these in our 96. We didn't even mean to, but I'm telling you we already did. In fact, we already counted it more than 1 time. You're like, what? How's that possible? Like, we didn't even touch that string. We didn't even touch that idea. Well, hear me out. We had 5 spaces, right, for each of the 5 characters of the string. And when we were constructing it here, we said 2 options for each place. So let's say, we have people P, Q, and R. Let's say we're excluding person P, so we're only going to assign the words to Q or R. And we have 2 options for each place. So in the first place, let's say we give it to Q, that's fine. Second one, let's say we give it to R. Third one, R. Fourth one, R. Fifth one, Q, right? That's what we wanted. And that's mostly what we got. But it's also possible that this case occurs, where the first choice we decide to give it to Q, the second one we also decide to give it to Q, and so on for all the other ones. In this case, 2 people are excluded, right? Which is not good. And in fact, we can also get, in this case, R, 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 R. So that's good in a sense, because now we don't have to worry about subtracting this out again. But like I said, we're actually subtracting these out more than once. And here's the reason why. In this case right here, we excluded P, and we counted R, 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 R in one of these 32 strings, right? We said there's 32 strings for each person that we exclude. We can also get this R, 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 R if instead of excluding Q, or instead of excluding P, we exclude Q. Because now there's still two options for each of these spots, but now it's between P and R, so we can still run into this case, which means that this appears in two groupings of these 32 strings. So we've subtracted it out twice. And the same thing goes for P, 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 and Q, 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 Q. So since we subtracted it out twice, we have to add one copy of each back into our sum. Because we did want to remove each of these, but we wanted to remove it once. So we have to add 3 more to our count, just to account for that double count. So our answer will be 243 minus 96 plus 3. That's going to be our final answer. And this is going to be 150, which will be choice B. So I admit maybe my explanation for this was a little bit tough to follow and a little bit tricky. But the principle and the takeaway about this question, the principle that this question is using is called the principle of inclusion-exclusion. So if this didn't make much sense, I encourage you to learn the principle of inclusion-exclusion. Oftentimes it has to deal with sets, so you have to define certain sets and compute it that way, which is totally fine and it works completely. I just tried to teach you the principle of inclusion-exclusion without those set definitions and sort of like logicking our way through it, which is not always great because it's hard to note that we double counted certain things. So if this question didn't make sense, I highly, highly encourage you to read up on that and be familiar because that principle comes up a lot as well. But yeah, that would be this question. Hopefully it made some sense. If you have some questions, feel free to leave comments and I'll get to them. All right, yeah, so that's question 23. Okay, so you'll have to excuse the sudden change in lighting, but I'm very committed to getting this video done, at least recorded. So we're going to move on to problem 24, and then one more question after this. So we're given a large square region is paved with n squared gray square tiles, each measuring s inches on a side. So in the diagram, we have these sides as s. A border d inches wide surrounds each tile. So, whoops, keep zooming in randomly. So the border here, what I drew in pink, that has length d, or it's d inches wide. And the figure shows the case for n equals 3. So n equals 3, 3 squared is 9, we do have 9 tiles. Then we're given when n equals 24, the 576 gray tiles, note that 576 is 24 squared, you can double check that just to be sure. The 576 gray tiles cover 64% of the area of the large square region. We've been working a lot with percentages in this video, so let's try to create a fraction whose quotient will equal 64% or 0.64. So when we're dealing with percentages, the numerator is like the quantity that we're interested in, and then the denominator is the total quantity. So in this case, the area covered, the area of gray tiles divided by the total area is going to be equal to 0.64 in the case when n equals 24. And we're asked to find the ratio d over s for this value of n where n equals 24. Okay, so what's the game plan here? We don't know what d and s are. We're going to have to somehow solve for them. And the only piece of information we have is this little fraction that we created here. So perhaps we can come up with formulas for the area of the gray tiles and also the total area that involve d and s, and then somehow solve for d over s from there. So the area of the gray tiles. Well, all of the gray tiles have the same area. That area is going to be s squared, since all of the squares have side length s. The total area of the gray tiles is the total amount of gray tiles times the area. So there's n squared gray tiles. So the area of the gray tiles is going to be equal to n squared times s squared. Good, so we have an s in our formula now, which is kind of what we wanted. Now we need the total area. And hopefully for this we'll use d. Well, the shape of the total area, like it's a square, right? We're given that it's a large square region. So to find that area, we just need a side length. So where we see this side length, this leftmost side length, I'm just gonna, I should probably do it in like a highlighter. That's not a very thick highlighter. This side here. We're gonna shift it to be somewhere in the middle of it, of the square. So we're taking this side, shifting it over, and sort of like drawing this perpendicular line in the inside of the square. And what we're going to do is we're going to decompose this line because we want to find the side length, and we know it's probably going to be in terms of s and d somehow. So this pink thing decomposes into the sum of these smaller pink lines that I'm drawing with these blue lines. Right? If we piece together those smaller pink lines with the blue lines as I drew, we get the same length as the large pink line. Okay, well each of the blue things has length s, because that's just equal to the side length of the gray tiles. The pink things are the borders in between the tiles, so those would have length d. So in this case, the side length, we'll call it L, is equal to d plus s plus d plus s plus d plus s plus d, or alternatively 3s plus 3d, or sorry, 4d. Okay, so that's nice when n equals 3. What happens for other values of n? Well, let's perhaps look at n equals 2. So what I'll do here is sort of erase that, and sort of draw these lines. And so what we're going to do is we're going to look inside of the pink region. And this pink region depicts basically the garden for n equals 2. So now there's only there's 2 squared gray tiles, so 4 total, and we have that border. So now the side length of the pink square, I'll call it L prime, is going to be d plus s plus d plus s plus d, which is equal to 2s plus 3d. So if we come over here, the side length here for n equals 2 and n equals 3. It seems that the length for just some random value of n is going to be equal to n times s plus n plus 1 times d. And maybe we can just check it. When you put in n equals 2, you get 2s plus 3d as expected. N equals 3, 3s plus 4d, good. Now we just have to convince ourselves of why this is true. Let's look back at the n equals 2 case. For each, we see that like there's going to be 2 sides of the gray squares that contributes to the overall side length. That's just due to the array format of these squares, that we're arranging them in a square. So it's 2 across, 2 down. So that's where we get these 2 s's. But we need to account for the border in between them. And we can't just say, oh, each square has a border above and below it, because if we're to do that, then we double count some borders. So for example, if we said that, okay, the top square has a border above and below it, and then the second square has a border above and below it, then we double count this middle border. So what if we just say there's a border above the square? So for this top square, the border is the one right above it. For this bottom square, there's a border right above it. So each square has a corresponding border right above it, but then we need one more at the very bottom to account for the bottom border that we didn't count. And that holds true when we consider the n equals 3 case, where for this square in the top right, we have a corresponding border right above it. For the next square, there's also a corresponding border right above it, and so on. And that's how we, construct this side length. So now we know that the side length of the large square is n times s plus n plus 1 times d, which means that the area of the total area is going to be that quantity squared. So it'll be ns plus n plus 1d squared. So now we have an equation, we have these two quantities that we just found that we're going to substitute back into our fraction, and we're in good shape because we have d and s. So let's see what happens when we do that. So in the numerator, we'll have n squared s squared. In the denominator, we'll have ns plus n plus 1d squared, and this should equal 0.64. You'll notice that the numerator is a perfect square. It's the square of ns, and the denominator is also a square. So we can take the square root of both sides. So we'll get ns divided by ns plus n plus 1d. Square root of 0.64 is equal to 0.8. What are we after? What are we trying to find? We're trying to find d over s. So we somehow want to rearrange the fraction until we have d over s. So I don't like dealing with decimals when especially we want to deal with fractions, so we'll just rewrite the decimal as 8 over 10. From here we can cross multiply to get 10ns equals 8 times the quantity ns plus n plus 1d. Cross multiply is the same thing as multiplying the denominator on both sides for both fractions. And let's simplify this a little bit to see what we get. So we get 10ns equals 8ns plus 8 times n plus 1d. 10ns equals 8ns plus 8nd plus 8d, something like that. And then we'll move the s terms onto the same side, so to the left-hand side, and keep the d terms to the right-hand side. So 10ns minus 8ns would be 2ns. That equals 8nd plus 8d. From there, we can factor out an s and d from both sides, so it'll be s times 2n equals d times 8n plus 8. And remember, we're solving for d over s, so we can divide both sides by s to get 2n equals d over s times 8n plus 8, but we'll also divide both sides by 8n plus 8. Cool, so we have our answer. D over s equals 2n over 8n plus 8. We just have to substitute our value for n, which in this case is 24. So this would be equal to 2 times 24 divided by 8 times 24 plus 8. That's equal to 48 over 200. What's the common factor? There's a common factor of 8 in between these. 6 divided by 25. We can't reduce that any further. That will be our answer, and that would be answer choice A. So perhaps the most convoluted problem we've done so far, but again, it's just about knowing what your variables are, creating the formulas that you need or that you know already from the problem, and just piecing it all together. Let's move on to the last question, which I think is actually easier than question 24, but we'll see. Rectangles R1 and R2 and squares S1, S2, S3 are shown below. combine to form a rectangle that is 3322 units wide and 2020 units high. What is the side length of S2 in units? So this side length will be 2020, and at the top we'll put 3322. Okay. What is something that's nice about squares that's not nice about rectangles? Squares have all the same side lengths. All four sides are the same length. Rectangles, we don't really know the dimensions and especially how they relate to each other, length to width, we don't know. So much of our focus will be focused on the squares. So let's just give the squares some side lengths. So for S1, we'll just say that all of its side lengths have length A. For S2, we'll give them B's. And for S3, it's C. We're given the length and width of the large rectangle. So let's see how we can create the numbers. Similar to in the previous problem where we took that pink highlighted line and we decomposed it into like the D's and the S's, we'll do a very similar thing here. So this is the line that we want to decompose, and we can decompose it into this blue line plus this orange line plus this pink line. And the reason why I broke it up like that is because the lengths I broke it into are very, very specific. Because we can slide these down and see that they are the side lengths of squares already within our larger rectangle. In fact, we can gather that A plus B plus C is going to equal 3322. So again, we're using this decomposition technique, or rather like a composition technique where we take smaller things and make a larger thing. Okay, that seems to be helpful. And remember, we're solving for the side length of S2 in units, so we're solving for B. So we have an equation with B in it, that's pretty good. Let's try to get another equation. And now we'll look at the height. Let's switch to pink. Okay. So that's the line we're working with. And there's a couple of ways to break it apart. Maybe you're tempted to first break it apart into this orange and this green, so that way the orange slides over to S1 and the green slides over there. The issue is that we don't really know the height of R1. If we knew that, we would be in business. But can we get that in terms of some of the other things? The answer is yes. What we need to do is consider another line. So I'll draw another pink line. And that looks like this, S3. And we'll do a blue line. And what I'm going to do is shift this blue line over and see that the blue line plus the green line equals the pink line. Okay, so we know that orange plus green is going to be equal to 2020. We just want it in terms of the variables. So orange is equal to A. And we're going to add to that green, and we're going to get 2020. But with what we just drew on the right here, we can express this green in terms of this blue and this other pink line. So this other pink line is now called C, because that's the side length of S3, and that's going to be equal to blue plus green, or alternatively, B plus C. Or sorry, not C, B plus green. So that means that green is going to be equal to C minus B. Let's substitute that back in here, and we get A minus B plus C equals 2020. let's remember the other equation we had. And, maybe you've learned this in school, and it's like, oh, if you have an equation with 3 unknowns, you need 3 equations to solve for the values. Sometimes that's true. And so you might be searching for a third equation, but we don't really have anything else to work with. We were given a length and a width, and we use them both, and finding a third equation would be kind of tough. So let's deal with what we have, and just see what happens when we add these 2 equations. Why am I adding these 2 equations? Because I see that they're very similar to each other. The only difference is the sign of b. So when I add them together, the b's will cancel. So we get 2a plus 2c equals 5, 3, 4, 2. Okay, and let's just divide by 2. A plus c is going to be equal to 2, 6, 7, 1, I believe. Cool. What does that mean? That means we can solve for b. Look at this equation right here. We have a plus b plus c. That's going to be equal to 3, 3, 2, 2. Well, we can rewrite that as b plus a plus c. And we just solved that a plus c equals 2, 6, 7, 1. And that's going to equal 3, 3, 2, 2. And remember, we're solving for b. So now we just have to subtract 2, 6, 7, 1 on both sides. And what we'll get is that b is equal to 651. And that's what we were solving for. Hopefully that's an answer choice. Indeed it is. That's choice A. That's what we'll roll with. And that is the solution. So that concludes my walkthrough of this AMC 8 exam. Hopefully you learned some things. I think the main thing for me was gathering what patterns are used, or like what techniques you should be familiar with. So remember, the things that we saw numerous times were averages, dealing with like a total amount of something divided by something else, knowing like what averages are, how to use them. Another thing were like percentages, being able to do arithmetic with percentages, but also do like conversions to decimals when needed, things like that. And at the very end, we saw a couple of problems where in geometry, we took a line and we decomposed it downwards. So those are the 3 huge takeaways that I can think of off the top of my head, but there are plenty more that we discussed in this video. Hopefully this was helpful. I'll try to do more of these in the future, perhaps for like the 10 and the 12, but surely some more for the 8. And yeah, thank you for watching. Hopefully this is helpful. Take care.